Hello, and welcome to part 3 of my AI lectures. In this lecture, we will be talking about learning machines and baby computers. This will be the lecture that is most focused on the philosophical dimensions of artificial intelligence, whether machines can think. You might have been thinking about the question of whether machines can think from the last few lectures, some of the examples we've gone over, like Deep Blue and Kasparov and so on. So there's a lot of issues at stake here, and I'm not going to be able to cover all of them. What I really want to focus on is Turing's discussion, and not even all of Turing's discussion. I really want to focus on Turing's responses to Lovelace's objection. This is one of the primary readings for this unit, Turing's Computing Machinery and Intelligence. This is a paper he wrote in 1950, just a few years before he died. He published this in Mind, which is a philosophy journal, but it's one of the more popular philosophy journals. It's one of the more widely read philosophy journals, most likely to be read by non-philosophers or people who are not just mathematicians and logicians. So this article is really Turing's attempt to communicate to a broader audience than he usually does. Around the same time, he had also had a couple of public appearances on BBC Radio, doing debates with other scholars about whether or not machines can think. Turing really took responsibility for computers and felt that he had some responsibility, especially for public communication about computers. There was a lot of misunderstanding in the early 1950s, just as these computers were starting to become more publicly known, having more role in public life, becoming commercially available. It was around this time that there were a lot of fears and sort of hype and skepticism and sort of science fiction rhetoric around these computers, and Turing felt like he had a responsibility to weigh in and not just ease fears, but really talk about what it means for machines to think. And so it's in this paper that he proposes his infamous Turing test, or what he calls the Imitation Game. This is his proposal for how to evaluate whether or not machines can think. You probably have heard about this test and know a little bit about how it works. And this is a paper where he proposes it. People have been talking about this test ever since. You might like the test, you might not like the test. We'll talk about the test in some more detail later on in this lecture. But the focus here isn't just going to be on Turing's test. And even talking about Turing, I don't want to focus too much on the test. I think understanding the test really requires understanding its role in Turing's larger view. And this is why I want to focus more not on the test, but on Lovelace's objection. If you haven't read this paper, I strongly encourage that you read it. This slide gives a little bit of a breakdown of the paper, or sort of the structure of the paper. So right off the bat, he proposes the Imitation Game as a better way of testing the intelligence of machines. In the next section, he explains how digital computers work and gives some discussion of his Turing machines and sort of the theoretical computer science that develops out of his Turing machines, which were developed 15 years earlier or so, in the 1930s, 1936. So in the paper, he explains how digital computers work, and then he makes a prediction, which is that computers will probably pass Turing's test, or the Imitation Game, or at least be generally considered intelligent by around the year 2000. He says in 50 years' time, and he publishes in 1950, so people take this as the year 2000. Since most people think that we don't have generally intelligent machines right now, most people think that Turing's prediction fails, but I want to look a little bit more closely at what Turing exactly predicts. And then after giving his prediction, Turing considers a bunch of objections, and the bulk of the paper, and most of the interesting discussion in the paper, comes out of his discussion of these objections. Now, these are not objections just to his Imitation Game. These are objections that are in some sense just in the discourse around thinking machines. These are the sort of popular arguments that are typically made around whether or not machines can think. So, for instance, the first one he considers is what he calls the Theological Objection, which is that God gave humans souls, but God did not give machines or animals souls, and so for this reason, animals and machines cannot think. Now, Turing obviously doesn't believe this, and this really has nothing to do with Turing's test. This is just a sort of popular view of machines and the question of whether or not machines can think, and Turing sort of weighs in on this question. I'm not going to go through all of these objections. Like I said, it's worth reading the paper and seeing how Turing deals with these objections, although I will just say a little bit about the theological objection. So Turing's an atheist. Turing doesn't believe in God, and he's not really entertaining this idea here. But his response to the theological objection is not to deny that God exists, Turing himself doesn't believe that God exists, but his response to this objection is not to argue that God doesn't exist, and so therefore machines can't think. He doesn't think that's going to be a very effective argument. Instead, he asks, if God is all-powerful, then why can't God give machines souls, or animals souls for that matter? Why do you think that giving a machine a soul is a limitation on God's power? Again, Turing does not think that God exists, but Turing's argument here is not to deny the premise of the question, but to show that even if you assume that that's what thinking requires, that doesn't show that machines are limited or restricted from thinking. If you believe that humans have a soul because God gave us a soul, then why can't God also give machines souls? I think it's important to reflect on Turing's answer here because not only to consider whether he's right or wrong about this objection, but really to get into his mindset of how he's thinking about these objections and how he's responding to them. He's not responding by denying the premise. What he's responding to, his response is to deny that premise doesn't apply to machines, right? So. And we'll see how that works in a little bit. But he goes through a bunch of these objections. Some of them are a little bit silly. Some of them he doesn't really believe. And some of them are very popular, maybe even still popular today. The argument from consciousness, the argument from various disabilities in particular. We'll focus on the Lovelace objection in this article, in this lecture. And I'll say that the Lovelace objection is the only objection that Turing discusses twice. Once in this section about... where he's considering various objections, and he gives a response to the Lovelace objection. But in this objection, he says explicitly that I don't think this response will silence my critics. And so at the end of the paper, and the final section of the paper, is where he again recalls Lovelace's objection, and he proposes to build learning machines in response. And so it's this proposal of learning machines in response to Lovelace's objections that really sets computer science down the path of machine learning that we see today in the recent boom in AI. And so this is the thread that I want to draw through these philosophical questions. I want to start, again, just to get into Turing's mindset, by considering the prediction that he makes in the paper. So this comes about halfway through, right before he gives... where he considers all the objections, and right after he's considered how computers work, how digital computers work. So he says, his paragraph starts off, it'll simplify matters for the reader if I explain first my own beliefs on this question. And the question is whether machines can think or whether computers can think. The first prediction that he makes is that in about 50 years' time, there will be computers with a storage capacity of about 10 to the 9. This should be 10 raised to the power of 9. For the record, Moore's law significantly outpaced Turing's prediction here, and we had computers that were significantly faster than 10 to the 9 bits of storage in 50 years' time, by the year 2000. But he says, so he makes this prediction about how much storage capacity these machines will have, and then he says, and I believe such machines will be able to play the imitation game so well that the average interrogator will not have more than a 70% chance of making the right identification after 5 minutes of questioning. So we'll talk a little bit more about how the imitation game works, but it's basically just a conversation that you're having with the machine. And his prediction is that the interrogator will not distinguish the machine from the human more than 70% of the time after 5 minutes of questioning. So the first thing I want to emphasize here is that his prediction it's actually a very low bar to meet. So this is not, can you tell that it's a machine after a long night's conversation, after hours of interrogation. No, this is just 5 minutes of conversation, just a sort of quick first impression kind of interaction. And he says that even then, after 5 minutes, judges will be getting the right identification 70% of the time. So the interrogator will be getting the right identification 70% of the time. In other words, the machine will be fooling the humans 30% of the time. So this is like it's a failing grade, right? So Turing is not predicting that machines will be as intelligent as human beings by the year 2000. What Turing is predicting is that machines will be clever enough that in your first impression after 5 minutes of questioning, you're fooled about 30% of the time. So this is not a very high bar to meet. Some might argue that this bar was met by the year 2000. But Turing goes on to say, and I think this is more important, he says, the original question, can machines think, he says, I believe is too meaningless to deserve discussion. Nevertheless, I believe that by the end of the century, the use of words in general educated opinion will have altered so much that one will be able to speak of machines thinking without expecting to be contradicted. So there's a lot going on here. First of all, he thinks the question, can machines think, is too meaningless to deserve discussion. This comes in the middle of a paper where he's arguing about whether machines can think. So obviously he thinks that it deserves some discussion. So there's a sort of riddle to unpack here. What does he mean by can machines think is too meaningless to deserve discussion? But then he says that by the end of the century, educated opinion will have altered so much that we'll be able to talk about thinking machines anyway. So what Turing's really concerned with here is not answering the question, can machines think, as like a scientific question. His real concern is about the sort of opinion that we have of machines. And he thinks that this opinion that we have is malleable. It changes. It alters over time. It changes over time. And he thinks that by the end of the century, we will have so much more familiarity with these computers that talking about thinking machines will not be such a shocking thing. And I think this is his real prediction, and I think he was right about this prediction. By the year 2000, people were talking about thinking machines in much more casual terms than was happening in the 1950s, when computers were first invented. Okay, so I want to get back later to this question about whether or not machines can think, and I want to talk about Turing's test and so on, but I want to focus right now on Lovelace's objection, and this came up in the last lecture talking about Kasparov versus Deep Blue and so on, these machines that are doing these awesome feats of what seem like intellectual skill, playing Jeopardy really well, playing chess or Go, beating players at StarCraft. When humans do this, we think the humans are really intelligent. We think they're smart. So if a computer can beat a human being at chess, Kasparov, we consider Kasparov very intelligent. Some people call him a genius because he can play very good chess. But if Deep Blue can beat Kasparov at chess, should we also call Deep Blue intelligent? So even before we get to Turing's test, you might wonder about what these demonstrations from machines imply about their intelligence or about whether or not machines can think. And one of the early objections that we already saw in the first lecture from Ada Lovelace was that machines don't think because we're telling them what to do. Right? So this is Lovelace's objection. Let me just repeat the objection again. So Lovelace says, the analytical engine has no pretensions to originate anything. It can do whatever we know how to order it to perform. It can follow analysis, but it has no powers of anticipating any analytical truths, relations or truths. Its province is to assist us to making available what we are already acquainted with. Right? Lovelace's point is that the machine is only going to do math, right? The difference engine, the analytical engine, is only going to do math if we set up the gears in just the right way to perform the operation, right? And so we need to know how to design the machine in order to perform that operation. And so really the intelligence is on our part as the designers of the machine, right? The machine can do anything that we know how to order it to perform. So the fundamental limitation on the machine, Lovelace is saying, is what we know. In other words, the machines are dependent on our own knowledge. So if the machines are always dependent on our own knowledge, the machines can only do what we tell it to do, then the machine doesn't deserve credit for its performances, right? Deep Blue didn't really beat Kasparov. Deep Blue's engineers beat Kasparov because they were the ones who knew how to program the machine in order to do all the clever things that it did. Deep Blue didn't beat Kasparov. Deep Blue doesn't get credit for what it did. All that Deep Blue can do is what we tell it to do. This is Lovelace's objection. And I think this is a very popular objection. People will often say, well, the computer might look clever, but it was just programmed to do that. Right? If it's only doing what we tell it to do, then it's not really an intelligent machine. This is Lovelace's objection. I think Turing considers this the strongest objection of all of the objections that he considers. And he talks about consciousness. He talks about a lot of other philosophically important issues. But he sort of dismisses all of them, and he takes Lovelace, I think, the most seriously, because he gives two different responses. So Turing's first response to Lovelace is just to say that machines sometimes surprise him. He's the one who's designing these machines and building the first machines ever that can do these sorts of tasks. But nevertheless, despite the fact that he's the designer of the machines, despite the fact that he's building the machines and telling it exactly what to do, the machine sometimes produces results that surprise him. if you've ever worked with any computers at all, sometimes computers do things that you don't expect. Sometimes you don't know why the computer is doing it. Maybe you even call technical support, and you ask the technician what's going on, and sometimes even the technician doesn't know. Sometimes the technician just says, maybe you just have to reinstall Windows or start from scratch. So just because these are design machines doesn't mean either the designer or the user has perfect insight into what they're doing. And because we don't have perfect insight into what they're doing, sometimes, these are real-world machines. Sometimes they break. Sometimes they have bugs. Sometimes it's the result of people doing a bad job in their design. And sometimes it's all sorts of other things. There's too much static electricity, and it shorted out a circuit or something. Lots of things could happen to these machines because they're real-world objects. They're not idealized systems operating in Plato's heaven. They work in the real world alongside us. And because these are real-world objects, they don't always do as you expect them to do. So this is Turing's first response. Sometimes machines surprise us. He says, a better variant of the objection of Lovelace's objection says that a machine can never take us by surprise. And he says this statement is a more direct challenge and can be met directly. Machines take me by surprise with great frequency. This is largely because I do not do sufficient calculation to decide what to expect them to do, or rather because, although I do a calculation, I do it in a hurried slipstart fashion, taking risks and so on. He says, I do not expect this reply to silence my critics. So Turing says that sometimes we make mistakes. So in theory, ideally, I could predict everything the machine would do because I'm the designer and I know everything that's going on inside the machine. But this doesn't actually work in practice, again, because the machine sometimes has bugs and defects that I'm not expecting. And sometimes also because I don't do my calculations correctly, the way that I'm anticipating what the machine does, the way that I'm reading the program, for instance, or the way that I thought that I built the machine isn't actually how the machine works, and so the machine ends up performing other than how I expect. So again, Turing's point, and this is I think confirmed by anyone who's ever worked with a computer, is that computers don't always do what we tell them to do. But Turing says, okay, so this suggests that if Lovelace's argument is just that the machine only does what we tell it to do, then Turing's response is a kind of response to that. No, the machine doesn't always do what we tell it to do. Sometimes it does other weird things that you don't expect. But this isn't a very convincing response, Turing admits, for a variety of reasons. Maybe the biggest reason is that this doesn't prove what we want it to prove, right? If we are talking about machine intelligence, it's not enough just to say that I don't anticipate everything the machine does. What we really want is for the machine to do something genuinely new, something genuinely novel, something more than just what I told it to do. More than just what I told it to do, plus any mistakes that I made in the calculations. Just because the machine runs into an error doesn't mean that it's intelligent. So this is Turing's first response, and it's not a very convincing response by his own admission. So he gives another response at the end of the paper in the section about learning machines. Turing recalls Lovelace's objection and then gives another response. And his response is not that the machine is really doing something new, but he gives a sort of method for making machines that can get around Lovelace's objection. Again, his response is to build learning machines. So he says, instead of trying to produce a program to simulate the adult's mind, why not rather try to produce one that simulates the child's? If this were then subjected to an appropriate course of education, one would obtain the adult brain. Presumably, the child's brain is something like a notebook, as one buys it from the stationers, rather little mechanism and lots of blank sheets. Our hope is that there's so little mechanism in the child's brain that something like it can be easily programmed. Okay, so Turing's second response to Lovelace's objection, if you say the machine only does what we tell it to do, his response is to build learning machines. So his argument here is something like, well, maybe it'll be easier to build learning machines. But maybe that's not a very good response. I want you to think a little bit about whether this is a good response to Lovelace's objection to build learning machines. And we'll come back here to consider Lovelace's objection and Turing's response, whether this is a good response. But as you're considering that, I want to give a sort of bit of historical background, a little bit of technical detail about exactly what's going on with machine learning today. So last time we talked about how computation works, and especially about moving in orderly ways through state space. So the old style AI that was very popular during the first golden age of AI, represented maybe most by something like Prolog or by the development of expert systems like Deep Blue. This has sometimes been called GoFi, a good old-fashioned AI. This is a term coined by a philosopher named John Hoagland to refer to this sort of old-style AI. The important facts about GoFi is that it's these kind of sequential operations, stepwise operations that the machine performs instruction by instruction. So in good old-fashioned AI, you have to tell the machine explicitly what to do at every step of the way, and like the only things that the machine can do on its own are very simple operations like add two numbers together or whatever. And what the programmer does is tells the machine how to perform a sequence of these operations in order to accomplish some larger goal, solving a program or computing the area of a circle or whatever. So the program is telling the machine what to do in terms of all these explicit simple steps, and the machine is performing all these steps in a sequential fashion, stepwise, one by one. Usually these steps are if-then statements, conditional statements, like so if this value is less than some number, then do this, otherwise do that. These sort of if-then branching statements is the core of programming. And this is sort of how GoFi is conceptualized, the way that old-style AI operates. One characteristic of this that harmonizes very well with Lovelace's objection is that in order to get the machine to do all these interesting things, you have to tell the machine explicitly what to do. All of the instructions to the machine have to be coded in advance. So the programmer has to have a very good understanding of the problem and exactly what steps are required to solve that problem in order to program a good old-fashioned AI. So if we're talking about GoFi, then maybe Lovelace is correct that anything that the machine does is something that we told it to do. But after the first golden age sort of died out and the AI winter set in, part of what happened when the AI winter broke is that we started doing new kinds of AI. And the new AI is not just sequential if-then conditional statements of the sort that you have to hard code by hand. Instead, the new AI, or sometimes called Newfangled Ai, this is also John Hoagland's term, Newfangled Ai, what is characteristic about Newfangled AI is that the machine learns, through its own sort of processes without giving explicit instructions. Usually, Newfangled AI involves massively parallel processing, so that lots of instructions are performed not stepwise and sequentially, but in parallel and simultaneously. And these parallel operations usually do something like train a network or train the weights of some statistical model in order to learn something that the programmers don't know in advance. So this is very important, and this will be very important for our discussion of ethics in the next few lectures. That with good old-fashioned AI, the programmer has to be an expert of what the machine is doing. And with Newfangled AI, you might be able to build a learning machine that does things that you don't know how it works, or that you're not entirely sure what it is the machine is doing in order to get its results. Because you're training the machine, sometimes the machine can learn things that you don't know in advance. This is characteristic of the second golden age of AI, especially with procedures or methods like neural networks or evolutionary algorithms. I'll talk about both of these methods in just a second. But let's start with neural networks. So the idea of neural networks is just to build a machine that operates like the human brain or like a mammalian brain. A brain, you might know, is made up of neurons. It's made up of a bunch of other structures also, but the core cell of the brain, of the nervous system, is the neuron. And the neurons have the cell body with these little dendrites that take in inputs from other neurons that are clustered around it. And then the cell body sort of generates a charge. And then once that charge passes some threshold, in other words, once it's sort of gathered enough charge from all of the other neurons firing around it, then this neuron fires. And the firing is done by sending an electrical signal down the axon of the neuron, and then it releases its charge out through the axon terminals. And these terminals, it should be noted, don't connect directly to the next neuron, but there's a little gap called the synapse, or the synaptic cleft, between where this neuron and the next neuron are. So they don't touch each other directly, but there's this little gap where one neuron. So it's an electrical signal through the neuron, but once it hits the end of the neuron, it releases a bunch of chemicals into the water, into the cerebral fluid around it, and then those chemical signals get picked up by the neuron on the other side, and that's how that neuron on the other side, through its dendrites, starts collecting a charge, and then once that neuron passes some threshold, then it fires, and so on. Part of the basic outline of the structure of a neuron is that individual neurons are rather simple. An individual neuron isn't doing all of the processing. Individual neurons aren't sort of minds on their own. The individual neuron is very simple. It's just firing or not, depending on how it's building these charges, depending on how the other neurons around it are firing. So what really matters about the neuron is not the structure of the neuron itself, so much as the patterns of connections between this neuron and all the other neurons. Now, this isn't exactly right. The neurons itself are doing lots of processing within the cell. The sort of computational power of an individual neuron is actually not trivial. How it's integrating all of the inputs that it's getting when it's deciding to fire, what are the results of that firing, especially in terms of how it grows to connect to other neurons around it. All of these things are very, very complicated, and but the sort of mathematical model of the neural network is to imagine that the neuron itself is very simple and that all of the complexity is really stored in the relationships between these neurons. So when we're building an artificial neural network, this is the idea. Every node in the network is relatively simple on its own, and all of the interesting structure comes from how this simple neuron relates to all the neurons around it, both the input neurons and the output neurons. Okay. So this is the idea of building a neural network, is to build a network of simple nodes that develop interesting connections with each other. Now, this has been tried for as long as we've been doing computers. I said in the history lecture that one of the early models here is the perceptron. The perceptron was an attempt at building a neural network by building a network of connections that could all adjust themselves with each other. So this is the structure of the perceptron. It's actually very simple, but the idea is that we have a bunch of input nodes, some data on each of these input nodes, and then each input node is weighted. So you times it by some weight, and each input has a different weight. And then what the perceptron does is it just multiplies each input by its weight, and then adds all those things together, and that's your output. It performs some function on that complete addition, and then that gives you your output. So the output is just some combination of all these inputs times those weights. Now, it's a very sort of simple structure, but the perceptron could learn to do some interesting tasks, and the way that it would learn is by adjusting these weights. So the weight is just how much this value matters to the overall function. So if this weight is higher, then this input matters more, and if this weight is lower, then the input matters less. And you can adjust these weights slowly. So the idea is that if you know what output you want, and you know what input you're getting, then you can start adjusting these weights so that you're more likely to get the correct output on the right input. And maybe the first couple of attempts that you do this, the weights are all off, and so you get really bad outputs, but you use the outputs in order to adjust. You sort of record the outputs, and you know what the ideal outputs are, and so you take the difference between the outputs that you get and the ideal outputs and use these to adjust the weights slightly, so that the whole thing gets trained up to more and more accurately get the outputs that you're expecting. I remember when I was in grad school, I was in a computer science lab, and we were programming little neural networks, little perceptron networks, to fly airplanes in a little flight sim, in one of the Microsoft flight sims. The idea is, again, that you have different routines for what the things that the plane does, like maintaining altitude over a long flight, and each one of the inputs are controlling. Each one of the inputs are taking information from different parameters, like its airspeed and its altitude and how much it's turning left and right and so on. And those are the inputs, and then you're weighting those inputs in various ways in order to get the output that you want. And the output that you want is sort of level flight, and so you can change these inputs. You can change the weights of these inputs in order to keep the whole plane steady. So these kinds of techniques have been used for for years, for decades, in order to build AI. Part of the problem, and I think I mentioned this in the first video, is that there's a big limitation to how well these things can work. This was made explicit in a book by Marvin Minsky and a co-author in the early 70s, I believe, right before, or maybe late 60s, early 70s, right before the Light Hill Report and the AI winter. And some people blamed the AI winter on the discovery of these failures, these sort of theoretical failures of the perceptron. The big lesson for the perceptron is that it can't learn nonlinear data. So here is, so imagine you have a data set. In this case, the data set is comparing domestication with size. So how big the animals are and how domesticated they are. I'm not exactly sure what the units on domestication are, but imagine this is the data set where we have, in this data set, we have some cats and some dogs. And your goal is to train a model to distinguish the cats from the dogs based on how big they are and how domesticated they are. And so if there's just two animals here, it's not so hard to draw a line that distinguishes them. But the issue is that as we add more animals, then drawing the right line to get all of the dogs on one side and all of the cats on the other side of this line becomes more and more difficult. And basically what we're doing is we're adjusting the slope of this line. As we're adding more animals, the slope of the line goes back and forth. Sometimes sort of teeter-totters one way or the other in order to make sure that we're classifying all the dogs on one side and the cats on the other. And the idea is that as we add more data sets, then this line becomes more representative of what this difference is. And so a well-trained model will a well-trained model will be more accurate in getting all the dogs on one side and all the cats on the other in this classification task, in classifying the cats from the dogs or distinguishing the cats from the dogs. And so again, what we mean by learning, that this model is learning to distinguish cats from dogs, is that it's learning the slope of the line that will divide this data set in half, such that all the dogs are on one side and all the cats are on the other. So the adjusting of this line is what the learning amounts to. And that's neat. And in fact, you can get the perceptron to classify some interesting data sets. But like I said, there are fundamental limitations here, which is most simply that this can only classify linear data. So the way that the perceptron works, just by adding these weighted values, is that you're only going to be able to basically adjust the slope of this line. The slope is just the weight of the sort of the vector of all these weights. So you can adjust the slope of the line, but you're never going to get a line that's anything but straight. So it might be straight with this slope, or it might be straight with some different slope. But however you train the data, you're only going to get straight lines. So if the data set is any more complicated than linearly separable, the perceptron is just not going to do it. The perceptron cannot classify nonlinear data. And this is a problem because all of the really interesting data sets, almost any natural system is going to have all sorts of nonlinearities that need to be dealt with in various ways. And the perceptron, it was clear pretty early on that the perceptron was not going to be able to do any kind of classification for anything more complicated than linearly separable data. Right? So if this data set had some dogs that were both smaller than and less domesticated than some cats, then there would be no line to cut the data set in half, and the perceptron just wouldn't be able to learn that classification task. So the perceptron failed to do this, and this was sort of the end of the first golden age of AI. Is one of the big things that led to the AI winter. But in the 80s, we figured out how to solve this problem. Some researchers working on neural networks, Rumelhart in particular, figured out mathematically that there was a solution to make the perceptron capable of learning nonlinear data. And in fact, it was proven in the 80s that a properly trained neural network was potentially Turing complete, which means it could do anything that any other Turing machine could do, which means that you could do any computational task whatsoever with a neural network. It was this discovery of the solution to the perceptron failure that started to bring AI out of winter and started to make theorists pay attention again, and eventually it led to the ImageNet solution by Greg Hinton in 2012. So what was the solution? What was the problem that was overcome? The problem was just you needed to have a hidden layer. So in the Perceptron, you have an input layer, and all those inputs are weighted, but they lead directly into the output layer. And what Rumelhart and others discovered in the 80s was that if you add more layers, at least just one other layer, and it's called a hidden layer not because you can't see it, but because it's just between the input and the output. What they discovered is if you add just one additional layer, such that the input feeds into the hidden layers, and then the hidden layers feed into the output. This is all that's required in order to get the machine to start classifying nonlinear data. In other words, you need internal representations. You need some intermediate representations. So here you see the basic structure of a feed-forward network. Again, you have inputs, just like the Perceptron. You have inputs, and they're all weighted, but in this time they're weighted in respect to some hidden layers. So this is a sort of very simple feed-forward network, very few nodes. But the idea is that every node in the next layer is connected to every node in the previous layer. So here the hidden layer is these 4 nodes, and this top node has a connection from all the inputs, and the second node also has a connection from all the inputs, and the third node also has a connection from all the inputs, and the fourth node also has a connection from all the inputs. And then the output layer has a connection from every node in the input layer, right? So this first node has a connection from every node in the input layer, and the second connection also has the second node also has a connection from every node in the hidden layer. So this is a fully connected feed-forward network. So it's fully connected because you have every node connected to every other node in the next layer. And it's feed-forward because the direction of flow only goes in this one direction. You go from the input to the output, and you don't have any sort of looping back or sort of feedback loops. So this is the general structure of the neural network. And again, the point is to weight all of these connections so that you can adjust the overall model to fit the data set that you're talking about. So here's a sort of elaborate and maybe a little bit scary model with a lot of numbers. But this is just the same kind of system. In this case, we have 2 hidden layers. We have a hidden layer here and hidden layer here. But these 2 hidden layers, all the numbers that you see are the weights of these various connections. So this is again a fully connected feed-forward neural network. And what we're doing is we're just adding up the weights of each input to construct these internal representations. So here's our first hidden layer. Here's hidden layer node 1. And then every one of these nodes is going to have some value, some weight. In this case, it's 8.4253. It's not really important to know what that number means directly. That number really doesn't have a meaning in itself. What that number has a meaning is in relation to all of the other numbers in this network. And the way that you get this number is by adding up all of the weighted inputs from the previous layer. So in this case, we have input 1, and then the connection strength here is minus 4.3942. So whatever this input value is, multiply that by minus 4.3942. And that's part of the value for this. But the other part of the value is input 2 times this second weight. The second weight is minus 7.4001. So the value here at 1 is going to be this value times the input plus this value times this input. And that gives you number 1. And then you do the same thing for all the other nodes in each layer. So we do for all these nodes, and then we get some values for these nodes, and then we take these nodes as input to the next layer, and we do another round of this fully connected weighting. And you do this a couple of times, and then you get your outputs. And your outputs will have some values. So this is what the internal structure of a neural network, an artificial neural network, looks like. What you're doing is you're adjusting the weights on this big connected network so that the inputs get modified at each step to produce some values at the output. So if we're doing, for instance, image recognition, if we want to decide whether this is an 8 or a 7 or whatever, what you might do is you might map each one of these pixels to one input. So here, this image has 784 pixels. So you need 784 input nodes. And then each 784 of those input nodes would be mapped onto several hidden layers that are all computing different relationships with those input nodes. And notice that a lot of these input nodes are just black squares. The actual data here with the 8, where the 8 is drawn, is only a small fraction of the overall image. But in order to interpret the whole image, you got to give it every pixel. And so it takes out all the pixels in. It starts doing some weighted sums in order to produce in order to generate the hidden layers. at each step. And eventually this will go to an output, and presumably if this is a number recognition network, for instance, then the outputs would have the values 0 to 9. And then this input, if it was a properly trained network, would give the output of an 8, because this is the correct answer would be an 8. So in other words, we're taking information about every pixel in this image, and we're producing as output some number. And if the network is trained correctly, then the number that it produces will reflect the number written in this image. So that's the idea. Again, this works. You can make very complicated neural networks that can recognize images of numbers very easily, can do general linguistic analysis, can to some extent understand the meaning of your words and produce its own language, do all sorts of interesting things. We'll look at some of these demos in just a second, but this is just the basic idea of how these things work. So adjusting the weights is where the learning comes in, small adjustments to these weights. And the way that this happens is with this algorithm called backpropagation. Backpropagation is a sort of fancy name for the algorithm, but the goal here is just to adjust the weights in order for the outputs to be the correct outputs. So this is what the training looks like. So this is the structure of the network, and then in order to train the network, what we want to do is find the correct weights such that you get the right answers for every input. You give it an input, and it gives you the right answers. And in order to train the network, in order to get these correct answers, what you want to do is use this backpropagation algorithm. So the way that backpropagation works is that you you start off from the bat with a randomized network. So just give all the connections, give all the nodes in the hidden layers some random value. If it just has a random value, then the solutions, the outputs that it gives, are not going to be very good. Garbage in, garbage out. But starting from that random set, what we're going to start doing is train, and by training, we're going to improve it incrementally, just improve it bit by bit, so that as we go, the solutions are closer and closer to being accurate. Ideally, at the end of this training process, if you give it an input, it gives you the correct solution at the output. But we start off randomized, so you're not going to get the correct solution right away. And what you do is you take the garbage solution that you get from this randomized network. So you get some garbage solution, and you compare that with what you know the correct solution to be. Right. So in other words, you take the expected output and you compare it to the desired output. Wait. That should not be expected output to desired output. That should be like the output you received to the desired output. So what output did you get? What output did you want? When you start off with a random network, the output that you get is going to be very different from the output that you want. But you can use the difference between the output that you get and the output that you want in order to make adjustments to the weights. If the output that you want is a bigger number value than the number that you get, then you might want to have the weights adjusted slightly to give bigger numbers next time you run it. Right? And this is the idea of backpropagation, is that you train it with data where you know the correct answers, and you use the error that you get between what the network produces and what the correct values are. You use that error in order to adjust the weights slightly, and you do this thousands and thousands and millions of times, and eventually, ideally, you get a network that is properly trained to produce the correct outputs from those inputs. In other words, what we're doing is we're trying to minimize the error. This is an error minimization problem. You start off with a very high amount of error with a random network, and over time, through this procedure of backpropagation, you minimize that error. Minimizing the error, this kind of task is sometimes called a gradient descent task. And you can think of it like a hill climbing algorithm. So imagine this is a topographical map, or this is a topological map where like this is a hill, this is the peak of the hill, and sort of we can walk up the hill. But the hill is not a perfect cone; it's sort of lopsided. So there's some paths that are longer, like maybe this is a longer path and this is a shorter path, but this is also a steeper path. Like we have to go more uphill on this path. This is sort of a flatter slope, but it would take longer to move all the way from this edge to the center. And so if we're trying to climb this hill, you might ask what's the best way to climb it, especially if we have some starting point. If we say that we're starting here, what's the fastest route to the top? It's not just going to be a straight line, because that doesn't take into account the elevation changes. But maybe this is the best route to the top. the goal here is to get as far from as close to the peak as possible in as few steps. But this is sometimes hard because finding optima is hard. Finding peaks and valleys in data sets can be hard. This is a problem of local optima. If we're doing gradient descent, we're trying to find a minimum. So say we have some function, here's the error function, and we want to minimize the error. So we want to find the lowest value for this function. So how do you know what the lowest value is, especially if you can't see the whole function? You might see where you are at some point and then see where you are close by. And if you're lower than you were close by, then maybe you're at a minimum. So this kind of, right, so if I hit this point, so if I'm going down this way, I can tell that I'm getting lower and lower and lower and lower, and then I hit the bottom of this little trough, this little local minima. Once I hit the bottom, and if I keep going, then I start rising again. So I was going down, and then I start rising, so that at that inflection point change is going to be a local minima. But it's not going to be a global minima. And the problem is, how do I find the global minima? Right, this is just a local minima. It's lower than the values around it, but it's not the overall lowest value in the function. I'd really like to get over here, but if I'm only checking a sort of short area around it, then I might not ever get over this this hump in order to see where the true global minima is. So this is part of the challenge of doing of training these neural networks efficiently, is trying to find ways of finding local optima quickly. Let me actually maybe I'll give you this little demo here of Jeff Hinton. Let me see. Let me come in here. Cam browser. Yeah. So this is a talk from Google. Google has their sort of internal talks where they invite speakers to give a talk. This was in 2007. This is a very long time ago, 13 years ago. This is maybe 5 years before the start of the recent AI boom. And this is maybe one of the time, this is sort of part of what helped start it off, is that they invite Hinton down to give a discussion of his neural networks. So in 2007, there weren't very many people working on neural networks. It was sort of a niche field. There were some scholars working on it. There were some theoretical successes around this time, but there were no big demonstrations of how powerful this stuff could be. But people were definitely working on it. And so Google invites Jeff Hinton to show what he's working on. And he gives an example of his neural networks, and these are sort of intermediate representations in his network. But he actually shows one of the first sort of successful image recognition systems. And I'll just show you this a little bit of this. He gives a demo, and I might let him talk a little bit.
Okay, there's that network. Here's where we're going to put images. Here's 500 features, 500 features, 2,000 features, and the 10 labels. First of all, we'll get it to do some perception. So I'm going to give it an image and tell.
Okay, so let me pause it here and just sort of explain what's going on. So this is the representation of Hinton's network, and these are the different layers in the network. And you see some of these layers are very big, and some of them are smaller. And each pixel in these images is giving you the value, whether the value is on or off, for all of these different connections between the inputs and the outputs. So here's one interface, and here's the other interface. And what's really interesting about this network is that the inputs and the outputs are reversible. So you can treat the outputs as the inputs, the inputs as the outputs. So in this case, in this first round of this demo, he's giving it an image of some number. So here he's giving it a 4, and that's being fed into this network. And then it's going to result in an output here. So this box is going to be the same as this box up here in the corner, which is just the numbers 1 through 9. So 0, 1, 2, 3, 4 on the top, and then 5, 6, 7, 8, 9 on the bottom. And so you'll see from this image, it'll feed through these layers, and it'll get some answer. So we'll go ahead and watch that.
Tell it to run forwards. Oops, sorry, I didn't mean that. I meant that. And you'll see these are stochastic. They keep changing, but it's very sure that it's a 4. See, those are the identities of these neurons. It knows that's a 4, and it has no doubt about it, even though its feature detectors are fluctuating a bit. If I give it a 5, hopefully it'll think it's a 5. Yeah, it doesn't have any doubt. So now let's be mean to it, because that's a lot more fun. I'm going to give it that. So it says sort of 4, 6, 8, 4, 8, 8, 8, 8, 8, 8, 4. it can't make up its mind whether it's a 4 or an 8. And that's pretty reasonable in those circumstances. It will actually, for that one, say 8 a bit more often than anything else. So we class it as getting that right. But it's very unsure whether it's an 8 or a 4. And just occasionally it thinks it can be other things like a 2. But it basically thinks 4 or 8. I can make it run faster so you can... It's basically 4, 8, and an occasional 6. I could give it something like this. And it thinks basically 1 or 7 and occasionally a 4. Because I programmed this myself, I want to point out that it's very reasonable for this. This is my baby. And it's very reasonable for it to think that might be a 4, because look, you can see the 4 in there. Okay. Okay. Now, that was just doing perception, but the very same model does generation. So what I can do is I can fix a top-level unit, and all I've done is I've fixed the state of one neuron. There's 1 million connections there, because that's 2,000 to 500. I just fixed this one neuron. But when I fix that state, then the weights, the 2,000 weights coming out of there to these neurons here, what they'll do is they'll lower the energy of the ravine for 2s, and they'll raise the energy of the ravine for all the other guys. So now we've got this landscape in which we've got all these ravines, but the 2 ravine has been lowered. And if we put it at a random point, it will eventually stumble into the 2 ravine, and then it'll stay there and wander around. So let's see if we can do that. So what's really going on here is I'm just going backwards and forwards up here. Ignore that for now. I'm going backwards and forwards here and letting it gradually settle until it's into a state that this network's happy with. So that's his brain state, and that doesn't mean much to you. If you look at that, you don't really know what it means. So what we're going to do is, as it's settling, we're going to play out the generative model here. We're going to do computer graphics to see what that would have generated. And so what you've got here is that's what's going on in its brain, and this is what's going on in its mind. So you can see what this is thinking. And I'm serious about that. That is, I know it sounds crazy. When I say to you, I'm seeing a pink elephant, what I mean is, I've got a brain state such that if there were a pink elephant out there, this would be perception. That's how mental states work. They're funny because they're hypothetical, not because I made a spooky stuff. So I use this language where the terms refer to things in the world because I'm saying what would have to be in the world for this brain state to be perception. Now, if I've got a generative model, I can take the brain state and say, well, what would have to be in the world for that to be perception? Well, that. So that's what it's thinking. That's its mental state right there. So you've got brain states and mental states. And most psychologists won't show you both. Let's go a bit faster. And it still hasn't settled into the 2 ravine, and now it's about in the 2 ravine. And now it's just wandering around in that 2 ravine, and this is what it's thinking. It knows about all sorts of different 2s, and it's very good that it does, because that means it can recognize weird 2s. Let's give it another one. It hasn't got into the 8 ravine properly yet. It'll jump out into other ravines because it's not really there. But by about now, it'll be in the 8 ravine. And it'll show you all the sorts of different 8s it believes in if you run it long enough. If you ran it for an hour now, it would probably just stay in the 8 ravine showing you all sorts of different 8s. OK. Let's do one more because I like it so much. Again, it's not really in the 5 ravine properly yet. Look, there was a 6. By about now, it's in the 5 ravine. And it'll show you all sorts of weird 5s, ones without tops and occasional 6s. And it ends up with a pretty weird one. But that's definitely a 5. And it's very good that it knows that that's definitely a 5, because it allows it to recognize things like that. OK, that's it for the demo.
All right, so just one more time. So this is an awesome demo, and this is part of what inspires Google to know that this kind of stuff actually works. This is 2007. This is only 5 years before the recent AI boom, and you can see how far advanced the top researchers in the field were just this short time ago. So we saw it do image recognition. You give it an image of a 4, even very weird 4s, or images of 8s, and it can tell you that it's an 8 or it's a 4. Sometimes it gets it wrong because the image itself is ambiguous. There's no real correct answer to what value it is, although you can train the machines to be more or less tolerant of different kinds of shapes. But the same model, the very same connection strengths, also does generation. So this last demo is him fixing the value of the node, right? So he's saying think about 8s. So he's saying think about 8s, and then he's running the generative model, and here is all the different 8s the machine can think about. These are not 8s that were drawn into the machine, right? So you weren't. It's not the case that the programmers drew every possible configuration that counts as an 8 and gave the machine all of the told the machine to classify those exactly as 8s, and only those. There are too many for pixel length this size. There are too many variations of 8s to have designers and programmers go through all of those. This is why things like image recognition were really hard to do with old-style AI, because if you're telling the machine explicitly what to do at every step of the way, then it's just really hard to get the machine to do anything of even mild complexity. But in this case, we're not telling the machine what to do at every step of the way. We're telling the machine how to learn, and the machine is doing things on its own. So the machine can generate lots of different 2s, ones that you may never have shown it before, ones you may never have told it were explicitly 2s. But the machine can infer from the other things it has learned that all of these things are 2s. So this is supposed to be a demonstration of machine doing something on its own, or doing something at least that we're not telling it to do. If you're interested in some of the history of this, of these neural nets, I recommend going through this presentation from Greg Hinton. Also, if you're into some of these technical details, I have this 3 blue 1 brown video on YouTube. It's actually the first one of a series of videos where he actually goes into the math of neural networks and what the neural networks are doing at a very basic mathematical level. And he walks you through every step of the way with this very visual learning style. I find this video series very helpful in understanding how neural networks work. For maybe a decade, I was teaching about neural networks to my classes before the big boom in AI, when there weren't a lot of teaching resources for this, and I had to draw little images of neural networks on the board. Luckily, we can do this stuff on our own, and in fact, I'm going to show you some demos in just a second. What else do I have here? So a lot of the advances since Greg Hinton's demonstration at Google in 2007 are just about building bigger and bigger networks. After Google hired Greg Hinton to lead their AI department, one of the things they've been doing is just building really, really big networks. You hear people talk about deep learning, and deep learning just means lots of hidden layers, lots of nodes in each layer. The biggest network that I know about is the outrageously large network, 137 billion parameters. There are 80 billion neurons in the brain. So this already has more nodes than there are neurons in the brain. As far as I know, this big network didn't do anything very interesting, and the general idea of training these massive networks isn't on itself producing a whole lot, although a lot of the major research is happening at companies like Facebook and Google and Amazon, where they have lots of computational resources to just throw hours and hours of supercomputer time at these problems in order to train up computers that can play chess or Go. Not every company has the resources to be doing these very computationally intensive tasks. And so a lot of the innovation since these early theoretical advances is about making the networks more manageable. There's lots of ways of doing this. One of the most popular ways, this is the technique developed by Jan LeCun called convolutional neural networks. And convolutional neural networks, instead of just going straight from the pixel array into a massive neural network, what convolutional neural networks do is they have this clever strategy of clustering images in certain ways and clustering the clusters and clustering the clusters. So these pooling algorithms that take certain areas of the image and build several intermediate representations for that part of the image. And the idea is that you do this for all different parts of the image, and then you can recombine these pooled resources into a much smaller neural network. Right? So the idea is that these convolutions make the image processing task much more manageable. And again, when Geoff Hinton beat ImageNet in 2012 to start the recent boom in AI, Hinton used the technique Hinton used were convolutional neural networks, exactly like Jan LeCun had described. So it's not just an intelligence technique, but it's really a data management technique. It's about making these huge data sets accessible to neural networks. And as computers have gotten better over the last 20 years, this kind of processing has also gotten better. A couple of other techniques that are very popular nowadays that deserve some mention. One is these generative adversarial networks, or these called GANs. So it's effective to build a neural network that solves some task and to train it to do that task. But even more effective and more efficient is to build a network that solves some task, and then you build a adversary. So the idea here is that you build two networks, one to do the task, and then an adversary. And the adversary's job is to try to fool the main network. The adversary tries to fool the main network, and so the network gets better by not only dealing with the data set, but also by dealing with this adversary. Using adversarial networks in order to train networks very fast has been a big part of the boom in recent AI. Over the last 5 years, adversarial networks have been very effective at efficiently training these big networks. Another kind of technique that's used, again, to manage these huge data sets in smart ways is statistical techniques, using statistics, using randomization or stochasticity, sampling techniques in order to manage big data sets. So this is one of the ways you get out of these local optima problems. So in this case, you have So the image on screen right now is you're trying to find the top temperature, the highest temperature in this data set. So this is a data set with temperatures going up and down, and there's lots of peaks and valleys and lots of local minima and local maxima, and you want to find the highest value. So one way of doing this, the least efficient way, is just going through the entire data set and keep track of how high the values go, and then once you get to the very end, you know that this is the biggest value. But that's relatively inefficient. You have to go through every single value. So the smarter way is to use a statistical method is to sample. This is a simulated annealing. So the idea is that instead of going through every single value, you take samples. You sort of randomly sample at different locations along the line, and you look at where values seem to be higher, and you use statistical techniques in order to narrow in on the best range of values. So there's just one highest value, and you can see that the line starts off by sampling all across the whole thing, but eventually it realizes that the highest value has to be in this range somewhere, and it eventually narrows it down until it finds exactly that unit, exactly that peak temperature, and does this by considering only a fraction of the overall timeline. Especially for something like temperature, when we know that there's not going to be radical discontinuous jumps, but it's all going to be sort of continuous up and down. This means you can use these kind of techniques to quickly home in on the best answer. Efficiently home in. This kind of statistical technique is also found in the Monte Carlo tree search used by AlphaGo in order to search the big Go space. It's too many possible games of Go to search them all, so you can use statistical methods in order to find the good places to search deeply. Another kind of solution to the computational complexity of these neural networks is just to build new hardware. So Google, over the last couple of years, have been releasing these things called TPUs, which are special purpose chips that are just designed to do massively parallel computations of the sort needed to train neural networks. It's already the case that the new phones are coming out with chips that are designed to do very fast neural network training. And there's all sorts of hardware companies that are just started up in the last year or two that the whole point of the company is to build new hardware specially designed for the computationally intensive tasks that are required to train these massive networks. So TPUs are one example of this. It's also the case that GPUs, your video card, your graphics card in your computer, also are very good at running massively parallel processes and tend to be very good at training these neural networks. So at Google or whatever, some of their supercomputers that they use are just massive farms of graphics processors all hooked up to do very fast processing. You can build a supercomputer in your bedroom if you buy enough video cards and hook them all up together. Okay, so these are a bunch of techniques for managing the big computational task of these neural networks. Here's a graphic representation of some of the different structures of these networks. So we talked about feed-forward networks and sort of deep feed-forward networks. There's lots of layers, lots of hidden layers, lots of nodes in each layer. But these aren't the only structured networks. There are other networks that have recurrent loops or loops from outputs back to inputs. These deep residual networks, these recurrent networks. There's also these convolutional networks that we've talked about, or deep convolutional networks. You can also build Turing machines with neural networks I talked about earlier. Markov chains, you can also think about Markov chains as a kind of neural network, the generative adversarial networks. But these are just different structures that are used in neural networks. They're sort of typically seen. This image is pretty old, but I'm not sure that we have a lot of new techniques aside from what you see on this chart. I might be wrong about that. If you know of techniques that are not here, I'd like to hear about them. Let me go ahead and show you a demo, though, to make this a little bit more realistic. Sort of bring it home. So this is the demo that you can get to by clicking that TensorFlow Playground link. TensorFlow is Google's neural network programming environment, programming language. You can use TensorFlow to build neural networks, and it's actually very simple to do this. You can build rather complicated neural networks in just a few lines of code. You have to then train those networks, and it's computationally intensive to do that. But just building the networks and how they get all hooked up is actually pretty easy. The coding of it is not so hard, and there's a lot of tutorials online for doing this. TensorFlow is one of the big languages. There's a couple of other languages that are being used for programming these neural networks. But TensorFlow, this is a programming language that DeepMind used to build AlphaGo and is using for a lot of their other neural network projects. But they released all the source code online, so you can use it to build your own neural networks. You can start playing with the code, and if you're comfortable with coding, it's not so difficult. But they also put this playground up as a little demonstration of how neural networks work. And what you can do with them. And so this is just a setup of a basic neural network. Here you can see are the different input features, the different features that we're considering. And we're considering this data set. And what we want is to classify the data set. In other words, to distinguish the blue from the orange dots. Since some of the dots are blue and some of the dots are orange, we only want we want the orange dots to be separated from the blue dots. And we want to use a certain amount of feature detection in some hidden layers in order to reach that conclusion. So I'm going to go ahead and just start this with the basic neutral default settings. And I'm just going to hit run. So I haven't changed anything on this map. This is exactly how the input starts. The input starts with these two features and then two hidden layers, one with 4 neurons and one with 2 neurons. And you can see that each of these internal representations divides the space in different ways. And you can also see that each node connects to all the other nodes in a feed, just like we would expect in a feed-forward network. So every one of these neurons is connected to the first feature here, and the second feature here is also connected to every single one of these neurons. And the connections, some of them are very light. You can maybe barely see that connection here because it's very light, which means it's not weighted very heavily. The thicker they are, the more heavily they're weighted. And there's also positive and negative weighting. So blue numbers are positive and the orange numbers are negative weighting. So you can see that some of these connections are going to be weighted very positively and some of them are going to be weighted very negatively. And some of them are not going to be weighted very much at all. So this is a very lightweight connection, not very strong connection. Okay, so again, I haven't changed anything about this network. This is just how you load up the default settings. But I'm going to go ahead and run it, and you can see that we went from a sort of amorphous no classification to very quickly circling all of the blue nodes and distinguishing those from all the orange nodes. And you can see also that the network itself changed. So some of these lines got thicker in the blue direction, some of them got thicker in the orange direction, and we built some new intermediate representations in these hidden layers. But the result is a classification of the data such that the blue are all on one side and the orange are all on the other. So this is a successful run, and it actually happened very quickly. It only took a few seconds. Let me do that again. I'm going to start a new one. Remember, every time you start one of these neural networks, you start with a randomized network. So every time I hit reset, we get a different configuration. And what that means is that our end solution is also going to be different every single time. You notice maybe that the circle drawn here is a little flatter on this end, a little pointier on this end. It's not the exact same shape that we got the first time. Also, the configuration of the overall network is not the same. The last time we had like a real big thick blue band and almost nothing coming off from the other one. But now the weights are distributed more evenly. We have a lot more orange connections here, right? So So this is really important. Every time you run a neural network, you're getting a randomized network. And then when you train that network, the goal is to get the right output, or to get output that satisfies your conditions. But it's not to get some specific internal structure to the network. In other words, lots of different neural networks might end up on the same result. Lots of different weightings of these connections might end up in a classification that's correct, that gets all the blue on one side and the orange on the other. In other words, there's several right answers to this problem. There's lots of ways of drawing this line. Here's one of them, and this is one network. If we run it again, this is a completely different shape, but it's also a valid solution. The network that learned this solution looks different than any of the networks before. Notice that all of these connections are now orange, right? So this network learned it in a way where it has sort of a negative weighting to all of these connections. So the internal structure of this network is very different from the internal structure of the network we just ran. And if I run it again, I'll get a different network also. This is, again, part of the point of these neural networks, is that you train them to do things that you might not know how to do yourself. I don't know the formula for exactly describing the oval that will separate the blues from the oranges. So I might be the programmer here, but I don't know what that formula is. But I can train a neural network to find that formula. And in fact, there's a lot of formula that are all compatible with the solution. And you can train neural networks to find all sorts of different formula in that range. Okay, so this is also a fairly easy data set. It's not that hard to distinguish. Let me give it, so you can go ahead and play with this. You can play with this by considering different features, different mathematical functions on that data set. You can also do things like add more hidden layers or add more nodes to each layer. The more nodes and the more layers, the more computationally intensive it is. The harder it'll be to get an answer, maybe. But for a sufficiently complicated data set, so look at this data set. This is a highly nonlinear data set. You can see the oranges and the blues are all mixed up in this swirl. So it's not just a simple formula that'll distinguish the oranges from the blue. So I've added some more inputs. I've added some more hidden layers and some more nodes in those layers. Let's see what happens if I run it like this. Okay, so the system drew a line here and has orange on top and blue on bottom, but this is not very good. You can see that there's a lot of values that is not getting right. All these blues should not be orange, and all these oranges should not be blue. And you can see that the system is trying to improve these results. It's trying to, oh, look, so it just did a big skew here. That got more of these oranges, but it didn't get these oranges, and it left all these blues still orange. So this isn't really that much better, but it's still improving. Oh, it's doing another big change here. So you're watching this network learn. Oh, now it's wobbling around. You're watching this network learn by making adjustments to itself in order to more accurately get the correct answer to this problem. In other words, to more accurately classify all the orange ones and distinguish them from the blue ones. And you see that it's getting better over time. It's making some choices that make it slightly worse, but then it improves. It's going back and forth. It's not certain. This is not a certain process. It's making guesses. It's going off in areas and seeing if that leads to improvement. And it really isn't leading to very much improvement here. It sort of looks like we got stuck. This is the best it can do. Any small improvement to the lines is taking it outside of this optimum. It got a little jittery there for a second, but it calmed back down. I want to say that what you're looking at here as this machine bounces back and forth along these different possibilities is making these different choices. What you're watching is a machine think. You're watching on your screen right now a thinking machine. It's not very smart. It doesn't get the right answer. It's sort of stuck here at a very bad answer. But it's not sure of this answer, and it's trying to change its mind. It's trying to improve. It's doing the best it can. The best can is not very good, though, so let's go ahead and stop, and let's see if we can do this better. Part of the problem is that we're not considering very many features on this input. So maybe if we consider more features, in particular, maybe if we consider some nonlinear features, like these combinations of the different data sets. Notice that every time I add a new feature, I have to connect all of those up to every single neuron in every layer after that. So now we have all of these very complicated internal representations. Maybe this is enough complexity to get that very complicated data set classified. Okay, so there's more activity. It's moving a lot faster because there's more connections and strengths to adjust. It's very uncertain. Machine's thinking. It's considering its options. It's not doing very much to improve, though. It's sort of wobbling along this little X pattern. It's not really getting much better than this. I can give it some time. Give it a little bit more time. I don't like it. Here's what I'm going to do. I'm going to turn this off. There's other parameters you can change here. You can change how fast it learns. You can also change the activation, the nature of the activation when the neurons fire. Sometimes this does things. You can sort of play with the different problem types. One thing I'm going to do here to try to get us out of these local optima is raise the noise. So noise is how much random information it's going to be considering. And the idea is that the more noise it considers, the less likely it's going to be to get stuck in some local optima. So here I'm going to try this. I don't know if it'll work. Sometimes this works really quickly. Sometimes the network is in a good position and gets it right away. Oh, this is getting a nice little shape here around those oranges and around those blues. It's not exactly right. It needs these oranges down here. But you can see that it goes through a lot more of these wobbling patterns because I've raised the noise. I've increased the randomness just a little bit, so it's not getting stuck in local optima. Whoa, is that the correct answer? Holy cow, look at it. It did it. All of those oranges are orange, and all of those blues are blues. Congratulations, little neural network. You did it. You did the correct classification. It took us a couple of tries. You can try this at home. This neural network is running on your computer. I can hear the fans on my computer start up because this is computationally intensive, graphically intensive. But it did it. It found the solution, making these small adjustments. You can try to do the same thing yourself. It's sort of fun to play with these demos of artificial networks because it's really showing you what's going on as you're training these networks, how it's constructing these internal representations, how it's sort of difficult to interpret what these internal representations really mean, but you can see that the overall network gets the correct solution anyway. All right. Let me come back to my presentation. Okay, so that was the TensorFlow Playground demo. There's other demos on online of these kinds of technologies and things they do. I used to have the Google quick draw demo up here of machines doing things. Actually, let me run Google quick draw. Do I not have it? I don't have it in here. I'm just going to run it because it's what I want to do. Here we go. So one of the demos that they use to demonstrate how their neural network technologies work. So this is quick draw. You can play with this. This is sometimes fun to do in class. So this is just in the browser. If you just look up Google Quick Draw, this is a doodle recognition thing. It's sort of like a Pictionary. So I'm going to draw. It's going to tell me to draw something, and then it's going to guess if I'm drawing it correctly. So it's asking me, can I draw a pizza? And then it's having its image recognition, see if it can recognize that I'm drawing a pizza. I have to draw it under 20 seconds. Don't laugh, please. Here we go. A pizza. I think I'm going to draw a slice of pizza.
I see triangle. Oh, I know. It's pizza.
Yep. Here's a fire truck. I think fire truck is a big like rectangle.
I see keyboard.
It's got wheels.
I see sleeping bag.
Maybe it's got a
or
ladder
bus.
Maybe a ladder on it.
Oh, I know.
It's
fire truck.
There you go. A frying pan. Got it. Frying pan has a circle.
I see circle.
Pan.
Oh, I know. It's frying pan.
Doesn't even very much look like a frying pan, but it's getting it. Penguin.
I see knee. Or nose.
Let's see.
Or paper clip. Or necklace. Oh, I know.
Oh,
it's
no.
penguin.
Wow. That's incredible. Coffee cup. Okay, here we go.
I see pond. Or cup. Oh, I know. It's coffee cup.
One more. Last one. Cannon. Cannon looks like
I see mountain.
that.
Or canoe. Oh, I know. It's cannon.
Hey, okay, so these are my drawings. They're not very good, but they were enough to get the machine to figure out what it is. Again, this is a machine learning thing. This machine is learning from these examples. We're training the machine as we're going, because everyone who's asked to draw pizza and then starts drawing pizza is giving the machine examples of what people think pizza looks like. So here are other examples that the machine has looked at that it thinks of as pizza. A lot of these pizzas look very similar to what I'm doing, but notice that they're all in different orientations. That some of them have the slice going up and some of them have the slice going down. Some of them have them to the side. Some are doing 3D effects. Maybe some of these other ones, fire truck. It's making guesses, fire truck, bus, school. Maybe this is its archetype of a fire truck, school bus. But here are other fire trucks that it's seen, other fire trucks that people have drawn. They all have a ladder on the top of them. That's interesting. And so these are all the different fire trucks that the machine knows. And so it can use these to train itself, so that the next time it sees a fire truck, it can use these to make a better guess about which one's fire truck. It sees something that looks like this, it can guess that it's a fire truck. Okay. Yeah, so that's quick draw, and that was the TensorFlow playground. Let's go back into the presentation. Okay, so this aside, so that was our aside about neural networks and machine learning. And this aside is all meant as an answer, again, to Lovelace's objection. Remember, Lovelace says that machines only do what we know how to order it to perform. And Turing's response is to build learning machines. So is Turing's response here any good to Lovelace's objection? Do learning machines show that machines don't just do what we know how to order to perform? Well, so a couple of things here. So one thing I want to say is that Turing's interpretation of Lovelace is not interpreting. So Lovelace is not objecting to Turing's test, but Lovelace isn't really even objecting to the idea of artificial intelligence, in the sense that Lovelace is not objecting to the idea that intelligent machines can do interesting things and do intelligent things. On Lovelace's objection, it can do whatever we know how to order it to perform. So there's all sorts of intelligent things that machines can do. In fact, I think Lovelace's objection is unique among all of the objections that Turing considers, in that Lovelace is the only one who doesn't outright say the machine cannot do certain things. Lovelace, in fact, is very open about what machines can do. Machines can do anything that we know how to order it to perform. Lovelace's point is not that there's some limitation on what the machine can do. Lovelace's point is that whatever the machine does is dependent on what we tell it to do. So the machine is not limited, and the way that I put this is that the machine is not limited in its intelligence in terms of what intelligent acts it can complete. Lovelace thinks that machines can do any intelligent act that we tell it to do. The limitation is on the fact that we have to tell it to do that. So what the machine lacks is not intelligence, but autonomy. The machine is not able to do anything on its own. Everything the machine does is something that we had to order it to perform. So machines are fundamentally limited by human knowledge, by what we know. So when Turing responds that we should build when he responds to Lovelace by saying we should build learning machines, what he's saying is that if a machine learns, it will be doing more than what we know how to order to perform. It will be doing more than just what we told it to do. It'll also be doing what it learned to do. And what it learned to do is not just, again, more of what we told it to do, but it's also part of what it experiences as it goes through its training sets, as it takes on new input and adjusts its internal structure to accommodate that input. The objection that Turing gives in the paper superficially seems like his point is that building learning machines, building the mind of a child, will be easier than building the mind of an adult. But he's giving this as an objection as a response to Lovelace's objection. And the response is not just that it'll be easier to program these machines, but really that the machines show that machines aren't all, that the arguments show that the machines aren't as dependent on human performance, human knowledge, as Lovelace's objection seems to suggest. Another way of thinking about this, here's an example I like, is the example of teaching long division. So if I'm a teacher and I have a student's never done long division before, and it's my job to teach them. So I have to run through some examples. The first few times I go through an example, I'm doing all the work. The student's not doing any of the work. The student's just sitting there watching me do it. And so, if you ask me, has the student learned? No, the student hasn't really learned. Like, maybe they've learned some things, but they need a lot more practice. It's going to take a while before learning actually happens. So when we start, the student is entirely following the teacher's instruction. But actually, that never changes, even as the student learns. So by the end of the learning process, the student has now learned long division, can do the task on their own. That doesn't mean that the student has come up with some new method for doing long division. even when the student has fully learned the task, the teacher still knows everything that the student is going to do. There's nothing that the student does in the process of executing the algorithm that the teacher isn't aware of in advance. Right, so the student is doing everything that the teacher told them to do. But we still give the student credit for completing the task. Maybe the student doesn't deserve much credit at the beginning of the process when I'm leading the example, when I'm sort of holding the student's hand through the example. Maybe the student doesn't deserve very much credit then. But eventually the student has learned and is owed credit for doing the task on their own, even if they're following the exact same instruction that I taught them as their instructor. And one of the ways that we test whether the student has learned is by seeing if they can do it on their own, by giving them like a quiz where they have to do it without my help or without the help of someone else. And if the student can do it on their own, we judge that they have learned and that they can do it autonomously. This is part of what this is part of the criteria we use to trust someone with the task, to trust. This is part of the process of maturity and reaching adulthood, is learning how to do things on your own and being trusted to carry those tasks out on your own. So Turing's response here about saying that we should build learning machines so that machines aren't just doing what we tell them to do. Part of the idea is that if a machine learns, then there's some sense in which the machine is autonomous, that it's doing something on its own, and it's not just doing what we told it to do. And that's even the case when, in some sense, the machine really is doing exactly what we told it to do, just like the student is following the exact algorithm. So if I give the student a new problem that the student has never seen before, obviously the student can do exactly what we did before in some other problem because that math won't work for this problem. So the student isn't just copying what happened before. What the student has learned is the algorithm for how to deal with the problem on their own. Right? You carry the one, you write the numbers down here, and so on. Learning that process means that they can carry that process out without the instructor holding their hand. That's evidence of autonomy. That's sort of what the goal is of the learning process in the first place. The reason that we teach students is so that they can learn things for themselves, so they can apply that knowledge on their own. So if we can build learning machines, Turing's idea is then we can get around this Lovelace's objection. So all of the neural networks that we've talked about earlier are supposed to be examples of these learning machines that are not just doing what we told them to do, but are doing something genuinely new, something that we didn't know how to order it to perform. Let me give you one more example of these kinds of learning machines that get around Lovelace's objection. This is not a neural network, though. This is with Evolutionary Robotics. In Evolutionary Robotics, we're not training a large neural network. Instead, the learning process is over evolutionary, using a sort of evolutionary mechanism. Right? The idea is that animals become more fit to their environment over time through processes of natural selection, where the poorly fit members die out and the more fit members live on and reproduce. So in Evolutionary Robotics, they're building robots that evolve in the same sense. The evolution here isn't the literal body evolution, so the robots aren't reproducing and then giving birth or anything like that. It's the same robot body, but what's evolving is the software. So just like in neural networks, the way the Evolutionary Robotics works is they start off with a random bit of software. The software doesn't have, it's not trained for any goals, it's just sort of random software. In this case, the tasks that they're performing is to try to find food, so it's sort of a biological task. They just find food, and they're on this little tabletop platform where at one end is a food bowl, and at the other end is a poison bowl, a food bowl and a poison bowl. And the food bowl charges their batteries, and the poison bowl drains their batteries. So if they go around the food bowl and they sit around there, their batteries charge up, and then they get food. And if they go around the poison bowl, their batteries drain out, and they don't get food, and they die off. So the initial run, so you have a bunch of these robots. They all have slightly different software, and then you run the first round. And because all the software it's all slightly different, but it's also all random. So the robots are basically going off in just random directions. The task that you're training them for is to go find the food. But when you start off, it's just random. They're not trained to do anything at all, so they just go off in random directions. But what you do is you decide that some of the ones have performed better than the others. You have some selection criteria. Maybe you say everyone who gets closest to the food. So maybe the 5 robots that get closest to the food, those are the ones that are successful. Those ones reproduce, and all the other ones die off and don't reproduce. And so then you reproduce, and you're not reproducing the robot bodies, but you're reproducing the software. So you take the specific software that was in the previous generation, and then you use that software to program all of the bots. So the next generation of bots are all programmed by the most successful software in the previous generation with some modifications. So you don't just, it's not just that same software in all the next generation, but it's that software with some modifications. And the modifications all look like evolutionary modifications. So you're swapping around some bits of code, or you're swapping around the connections between these codes. So you're doing different things, sort of these evolutionary operations that are supposed to, in some sense, mimic the kinds of operations that are performed on DNA in evolution. So, you're flipping a string of a string of genetic code, or you're swapping a piece of genetic code out, or you're swapping a piece of genetic code in. Right? Different things you can do to the genes randomly, but so that the next generation is slightly different from the generation before. And you're doing the same thing with robots. Each generation is slightly different from the one before, and it inherits traits from the most successful of the previous generation. So when you start off, the robots go randomly, and none of them get anywhere near the food, but you take some of them, you consider them the most successful, and you breed them to the next generation, and you do this over hundreds or thousands of generations. And eventually you get robots that go basically straight to the food. The robots have been trained and have survived the selection pressure over hundreds or thousands of generations, so that the robots, you start them off and they basically go straight to the food. So this is pretty cool. You can train robots to do things without actually, right? So you're not programming the robots to find the food or go to the food. You're just having the robots sort of succumb to these evolutionary pressures. But eventually you get, if they're working within these evolutionary pressures, if you apply some selection pressure, then you eventually get robots that are very good at the task, that go straight to the food. And to show how good at the task, and especially to emphasize how the performance of these robots is independent of what the programmers are telling them to do, is that some of these robots learn to lie. So this is a paper from 2009, so well before the recent boom in AI. So these researchers are programming these robots to go to the food, and one of the tricks here is that there's limited space around the food, so not every robot can fit around the food. So it's not just can you find the food, but can you find the food quickly before the other robots? If you don't find the food quickly enough, then all the space will be taken and you don't get any spot around the food. So only the fastest, so eventually the robots are good enough to get to the food, but then eventually it's only the fastest robots survive. And then one generation, they found a robot who discovered a trick. And the trick involves understanding a little bit about how these robots orient, or how they know where they're going. They have a little camera on top, and they are moving with respect to the images, the colors that they see around them. So the ones that are most successful are the ones that are following the lights for the food, and the food glows a particular color. It glows a different color from the poison. But also, the robots are programmed to themselves glow different colors depending on whether they're wandering, whether they're being poisoned, or whether they're eating. So you can see that the wandering ones are green, and the ones that are eating are blue. So one really good way of finding the food for the robots is to look for the blue lights, because if you look for blue lights and the blue lights indicate that the robots are eating, so that means that that's where the food is. So if you go towards the blue lights, you're going to go towards the food. So one successful strategy is find the blue lights and go towards them. And so a lot of these robots were using this strategy of finding the blue lights and going towards the blue lights in order to be successful at this task. And then one robot figured out that in order to make sure that there's room at the food, one very clever strategy is for the robot to go out towards the poison bowl and then start flashing blue. It starts flashing blue, and so the other robots who are looking for blue see that blue light, and they all go to the poison bowl. And that leaves plenty of room around the food bowl for this robot to go back to the food bowl and charge itself up as much as it needs. So this is deception. The robot was deceiving the other robots by flashing a signal that was not true, but that took advantage of their disposition to follow that color in order to make room for itself around the food. Right, so this robot solved, in some sense, the robot gamed the evolutionary system. Was trading on the gullibilities of his conspecifics. So the point for our purposes is that these robots evolved to lie. This was a strategy that they discovered on their own. It was an available strategy, but the researchers who built these robots were not expecting that these robots would learn to lie or would evolve to lie. They were just as surprised to see this kind of behavior themselves. Right? This is not a behavior that the programmers put in explicitly into the machines. It was something that the machines could discover given the programming that they had, but it was not something that was directly programmed. It was something the machines learned through their own evolutionary process, through this natural selection process. So the claim is not that the programmers had nothing to do with this, but just that the specific task, in particular the lying, is not something that was directly programmed by the designers, which means that, again, it's supposed to be an example of the machines doing something other than just what we told them to do. They're doing something on their own, that they've learned on their own. Okay. So this is not an argument that these machines are intelligent or intelligent like people, or it's not an argument that they have free will or anything like that, that they're conscious. These machines are not conscious, or have minimal consciousness, if any consciousness at all. These machines are just doing this very simple task, but performing the simple task is enough to both escape the explicit intentions of its designer, to go outside of what it's programmed to do, and so they're a counterexample to the Lovelace objection. So I've given other arguments that machines can think in one of the earlier talks where I was going over this background of how computers work. I gave a sort of Turing-inspired argument on the basis of the universality of Turing machines. I'll give that again right here. If the brain is a machine that thinks, if the task that the brain performs is thinking, and a universal Turing machine can perform the work of any other machine. In other words, if the brain is a machine and Turing machines can do the work of any other machine, then a Turing machine can think. If the work that brains do is thinking, and Turing machines can do the work of any other machine, then Turing machines can do the work of thinking also. So I think this kind of argument is implied by the universality of Turing machines. You need to show that thinking is the kind of process that can be performed in a formal way of the sort that universal Turing machines are capable of performing. But I don't think that's such a hard barrier to entry. I think the point here is just that Turing machines can do anything that any machine can do. Maybe in different time, maybe it requires different time or requires more memory or something. But the universality of Turing machines implies that if the brain is a machine, then universal Turing machine can do the same work that the brain does. I think this is a Turing-inspired argument. Turing never actually gives this argument explicitly, but I think this is the kind of consideration behind Turing's own belief that machines can think. But this is not the argument that he gives publicly. He gives his Turing test argument. Before we get there, I want to give another argument that machines can think. I know I'm running over time, but I'm going to do it anyway. Another argument that machines can think. This is another argument based on the nature of computation, not inspired directly by Turing, but inspired by some of our discussion of what computers are, how computers work, especially that computers can be represented by state machines, or at least the program of a computer can be represented by a state machine. So here's the argument. So the argument is babies are... the real argument is that you're a computer, but the way we get to the argument that you're a computer is by arguing that babies are computers. By a baby, I mean an infant, let's say less than 5 months old. 5-month-old infants are not doing very much on their own. They're doing some very basic tasks, like crying and laughing and sleeping and pooping. But they're not as complicated as you are. But the argument here is that if I can show you that babies are computers, nothing changed about your computational nature from when you were a baby. We were all babies in the past. If babies are computers, then we were computers, and nothing changed about the fact that we're a computer. So if babies are computers, then, or if we were computers when we were babies, then we're still computers now, and so we're a computer. So the big move in this argument is to argue that babies are computers. If I can convince you that babies are computers, then hopefully that makes it at least more plausible that you're a computer. And the way that I'm going to argue that babies are computers is based on this idea of a finite state machine. We talked about this last time. This is the core of the program of a Turing machine, is this finite state machine. And the finite state machine is just that there's a certain number of states, and there's a certain number of operations that you can perform on the machine. In this case, with the turnstile, you can push through the turnstile, or you can put a coin in the turnstile. If the turnstile is in the lock state, pushing through does nothing. But if it's in the lock state and you put a coin, then you go to the unlock state. If you're unlocked and you put in a coin, you stay unlocked. But if you're unlocked and you push through, you go to the lock state. Right? So different operations move the system from different states, from one state to another. Moving between states is a kind of computation. It's kind of orderly operation, and this is what computation really is. Right? So this is the computational description of the operation of this turnstile. Notice this doesn't have anything to do with binary code or wires and transistors. Right? This is not computation in the sense that your desktop is a computer. Right? This is computation in the more general sense of orderly operations of a finite state machine. To maybe give another example of a finite state machine that's in the direction maybe somewhat closer to the way that you're a computer, the way that baby's a computer, is a spinning top. So a spinning top, you can make a spinning top out of a block of wood. You just whittle the wood down to have a point at one end. So a spinning top, it doesn't need to be a mechanical device of any complexity. It doesn't need to have any kind of internal structure. It can just be a block of wood that's carved in the right way. In fact, a block of wood that's not carved can also spin for a little bit. It's just not going to spin very well. What makes the top a computer is that it's a state machine, that we can describe what the states of the top are and how it moves between these states. So for a top, if you know anything about top physics, the ideal spinning top is perfectly upright, is not wobbling at all, but it's sort of perfectly around a vertical axis. And this perfectly vertical spin in the jargon is called the sleep state. It's sleeping because it's not moving, even though it's sort of standing upright. So the sleep state is the ideal state when it's perfectly vertical spin. The other obvious state to talk about is the stop state when it's not moving at all. It rolls to a stop and sits on the table motionless. So the stop state is another state of the top. And we know by entropy, just the way that these systems work, is that you can spin it up, but eventually it'll stop. It's not going to go on forever. It's not a perpetual motion machine. So you can try to spin it, but eventually it'll end up in the stop state again. So the stop state is kind of this universal attractor. No matter what motion you put onto the top, it'll eventually roll down into the stop state. And the idea is that the ideal state is a sleep state, and we can do certain things to the top to make it move towards the sleep state. And then it'll move back to the stop state back on its own. What you do to move it to the sleep state is you spin it. So you a little flick of the wrist to spin it up. When you spin it that way, you're increasing the angular momentum. You're decreasing the precession. You're making it go closer to vertical. But you're spinning it faster will make it go closer to vertical. So spinning the top is what moves it from the stop state towards the sleep state. Maybe it never actually gets to the sleep state. Maybe it gets close and then falls back down before it actually hits a perfectly vertical spin. Maybe you didn't flick it in the right way and it just wobbles. It starts wobbling immediately and then stops soon afterwards. Right. So there's various gradations between the stopped and the sleep state. Right, so this is part of why this is a more complicated example, because the top is a dynamical system. Even though there's no internal complexity to the top, even though it's just a block of wood, the way that the top moves between the stop and the sleep state is dynamically complex. And different tops, different structures of tops, are going to move between these states in different ways. And the transition between these states is going to be continuous. Right, so it's not just an on or off state, but it's sort of slight continuous changes in angular momentum. If you're increasing those changes, then it's going to reach the spin state, and if those changes are decreasing, then it's going to go back to the stop state. So here I'm just representing two states, but you can imagine that it's sort of a continuous process from one state to the next. So it's not just two states, but sort of an infinite number of states that the top moves through. But this, if it's still moving through these infinite number of states in an orderly way, even if it's a continuous process, even if the operations themselves are continuous, the fact that it's moving through these states in an orderly way, that you can relate the physical forces to how it's moving in the state space. This is, I want to argue, this is what makes it a computer. It's performing orderly operations by navigating through a state space. This is what makes it a computer. The top's a computer. So if you can accept that the turnstile is a computer and the top's a computer, then the baby computer shouldn't be that hard. If a computer is just orderly operations within finite state space, then in order to figure out what computer the baby is, you need to figure out what states the baby moves through, what the different states are, what the operations are. So what are the states of a baby? If we're talking about a 5-month-old baby, like I said, it's not very complicated. It's crying, it's eating, it's vomiting, it's pooping, it's sleeping, it's laughing. This is not a complete list. You can imagine putting other states on here, maybe growing, maybe screaming. Maybe screaming is a slightly different state than crying. But my claim is not that I've listed all the states of the baby, but just that we can imagine listing all the states of the baby. It would be something like this, right? We can, if we sit here for a few minutes and think about what states babies can get in, 5-month-old babies. They're not doing all that much complicated things. Here's a list of things. We can imagine expanding out this list, but it's probably not going to get much bigger than this because babies aren't doing that much. So now we have a bunch of states that the baby goes into, and what really matters for the computation for orderly operations is the operations that you perform from one state to the next. So, I have a baby that's crying, and I want the baby to get into the sleep state, and so the way that you get the baby to move from the crying state to the sleep state is by first feeding it, and then maybe burping it and changing its diaper, say, and going through this process, performing these operations on the baby, moves it from one state to the other, and you sort of can see how the baby's computing its various states. It's the computation here is sort of what is it doing based on the state that it's in and the operations you're performing. I want the baby to get into the sleep state, so I have to perform this series of operations, moving it from this state to this state to this state until it's finally in the state that I want it in. Now, this might seem a little bit weird to be thinking about babies as computers in this way, but I want to argue, and I want to be serious about this, that this is really a lot of how people already intuitively think about babies, sort of our sort of knee-jerk intuitions for how to raise a baby and what you're supposed to do with babies. It's about this kind of stuff, like a young couple, first-time couple having a baby, is really thinking about what is the baby doing and what do I want the baby to do and how do I get the baby to go from doing this thing to doing that other thing. The baby is not sleeping and it's just screaming. What do I need to do? Maybe you need to feed it. Maybe you need to change its diaper. Maybe you need to do some other things. But you're thinking about, with real human babies, you're thinking about what operations to perform to get the baby to do what you expect it to do or what you want it to do. And again, this is not the complete baby map. I haven't given you all the states of the baby. I haven't given you all the transitions that babies can go through, all the different operations you can perform. I'm just trying to be suggestive here that what it would mean to describe the baby as a computer is just to give this complete mapping, to describe all the states, all the relevant states, and describe all the operations that the babies perform that move it from state to state. If you can give this map of the baby, then you've described the baby as a computer. You've described the baby as a finite state machine. That's all it means to be a computer. Again, I'm not trying to convince you that babies are anything other than what you expect. I'm not trying to. This is not an insight into what babies are. Babies are the same little creatures that you are familiar with. What I'm trying to give is insight into what computation is, or what it means to be a computer. We often think about computers as those things on our desk, those bits of technological artifact that cost a certain amount of money or whatever, high-tech things. But that's not what computation is in the most general sense, in the sort of deep mathematical sense. In the deep mathematical sense, a computer is just something that performs orderly operations. And so anything that you can describe as performing a sequence of orderly operations, that's just what it means to describe that thing as a computer. What it means to describe something as a computer is to describe it as performing a series of operations. So babies are computers in the sense that babies perform a series of orderly operations. And by that same logic, you are also a computer. You are a state machine performing a series of operations that move you from certain states to other states. You are a much more complicated state machine than your baby. I have states like I'm worried after paying rent that I'll have enough money to eat for the month. Say. This is not the kind of state that a baby can get into. This is the kind of state that requires sort of sophisticated emotions and cognitive capacities and probably requires language. These are not the kinds of states that the baby can get themselves into. I'm a much more complicated machine. I have much more complicated states and much more complicated transitions between these states. But the difference between me and the baby is just how complicated this state machine is. That I'm just a more complicated version of the same thing that the baby is. And maybe to some extent I'm sort of built on top of this state machine. Like there's also times where I'm crying and there's things you can do to make me go from the crying state to the eating state and so on. So maybe we're all machines like this. We're all computers like this. It's just easiest to see that the baby is a computer. All right, so that's my argument. I know it's a little bit wild. I know it's not immediately convincing. The goal of the argument is to really break our habits of how we think about what computers are. You might have all sorts of objections. You understandably would have objections to this kind of argument. Let me just talk about a few of these objections. These are common objections. So one objection is that maybe babies are too complicated for this. Maybe babies don't have just a finite number of states, but maybe they have an infinite number of states. Right? Maybe the problem with the argument is that I'm assuming that babies can be described by just a finite number of states, but really babies have infinite states, and that's just a much more complicated system. Okay, so maybe babies do have infinite states. Well, maybe infinite states are in some sense impossible because there's only a finite amount of stuff in the universe, only a finite amount of time that I have, so maybe infinite states in some sense are impossible. But we can imagine extremely high numbers of states, right? So the very simple model that I give here, it's obviously oversimple, and we can imagine a much more complicated model with an indefinite number of states, maybe very high number of states. But that's fine, because the theories of computation allow you to approximate any infinite state machine or very high number of state machine with a PDA, with a finite state machine. Right? In other words, this same basic model of computation dealing with finite number of states can be extended to deal with an infinite number of states or an indefinite number of states. So the fact that babies might have an infinite number of states or an indefinite number of states doesn't mean that they're not describable with finite state machines, or describable in the way that these theories of computation work. Here's another kind of argument, sort of along the same line. Maybe not an infinite number of states, but maybe instead of discrete states, they're continuously changing states, something more like the top. But again, even if babies have continuous states, continuous transitions between states, even if we consider that the baby is an analog computer, it's still a computer. You can have analog computers. The top example is supposed to be an example of an analog dynamical system that's still computational because it's still performing orderly operations in state space. So even if babies have infinite number of states, even if they have continuously changing states, we can still model that with a finite state machine. We can still model that as a computer. Another common kind of objection is the randomness. So maybe babies are not deterministic computers, right? So sometimes feeding the baby will stop it from crying. Other times it won't. Sometimes some babies behave differently than other babies. Not every baby behaves the exact same. And again, that's true, but that doesn't change the argument here about babies being computers. Because even a non-deterministic system, so you can build a basic model of a computer that's deterministic, that goes from one state to the next by some set of operations, but you can also build non-deterministic computers. A non-deterministic computer doesn't necessarily go to the next state based on some operation, but might go to that state with some probability. So when the baby's in the crying state, maybe there's a 40% chance that you can move it to the eating state, but maybe sometimes it just refuses to eat, and there's a 60% chance that it moves to the pooping state. And whether it goes for one or the other is just a dice roll based on these probabilities. So this is going to be a non-deterministic system. How this system behaves is to some extent random, and it's based on the probabilities that structure its finite state machine. But again, that's fine. You can build stochastic or random non-deterministic state machines, and you can model non-deterministic state machines with a deterministic finite state machine to arbitrary precision. It's very inefficient to do that, but you can theoretically do that. The fact that babies might be random or stochastic is not a constraint on this argument. Maybe it's better just to spend a little bit, last thing to say. One thing to think, do I write this? No. One thing to think about is what would it mean for the baby to not be a computer? If what a computer is something that performs orderly operations, even if they're orderly and random, as long as it's performing a sequence of orderly operations, then it's a computer. So what does that mean? What does that imply about the claim that babies are not computers? In other words, if you think that babies are not computers, if you're committed to the claim that babies are not computers, and I tell you that a baby, and I tell you that computers, what it means to be a computer is to be a state machine with memory. But you're committed to the idea that babies are not computers. So what does that imply? Well, that implies that babies are not finite state machines. So what is the alternative to a finite state machine? Well, the alternative to a finite state machine, because we can do non-deterministic state machines, because we can do continuous and infinite state machines, none of those are alternatives. The actual alternative is to say that babies have states, that there's no orderly operation that they have to get into or out of those states. In other words, imagine a free-floating state. So here's a state, or here the blinking state. In the representation I show here, it's not complete, but I don't show any pathway into the blinking state. There's no operations that you could perform that get the baby into the blinking state. Now, what that means to me is that this model is incomplete, that there's some transitions that I haven't fully specified. But you might also think that, well, maybe the baby's not a computer, which means that maybe it has these states such that there's no orderly operation that you can perform that can get it into those states. But maybe the baby ends up in those states anyway. So in other words, the claim that babies are not computers is equivalent to the claim that there's some states that babies can perform that there are no orderly operations to get them into those states. I want to say this is analogous to a kind of miracles argument, that babies can do things that no machines can do, or that babies can do things that cannot be explained by any mechanical process. If you're saying that a baby's not a computer, you're saying that there's no possible mechanical process or no possible process that any machine can go through that will do the same thing that the computer is doing. And I want to say that that's it's equivalent to suggesting that there's a miracle, that like a miracle cure. Sometimes when I say that a miracle's happened, I just mean that it's a really great thing. If I have cancer and then my cancer goes away, I might say it's a miracle. Not because I think anything magic happened, but just because I think it's a great thing. It's something I'm very happy that it happened. I'm very glad happened. So it's a miracle. It's just a sort of statement of I'm glad that something positive happened. But sometimes I might mean miracle as in something magical happens, something that cannot be explained, something that defies any explanation. And what I want to say is that if you're saying that babies are not computers, you're saying that there's some operations that the baby performs that cannot be explained by any mechanical process. In other words, that there's no explanation. In other words, that the baby's performance is miraculous somehow. Miraculous not just in the sense that it's good, but miraculous in the sense that it's unexplainable or sort of simply cannot be explained. And I want to be skeptical of those kinds of claims. I think that if you believe in science at all, if you think that scientific explanations can be given of how babies operate, then you must believe that babies are computers. Then you must believe that there's some set of mechanical operations that the baby's performing. Maybe they're not operations at this level of abstraction, and it's important that I'm operating at a fairly high level of abstraction, like eating and crying and vomiting. Those are very high-level descriptions of behavior. I'm not talking about, what every molecule in the baby is doing or what every cell in the baby is doing. I'm not talking about even microbiological processes or anatomical processes like the crying involves, screaming, and it involves wiggling around, it involves tears coming out of the tear ducts. There's all sorts of mechanical, anatomical processes in the eyes that make the baby cry or makes the baby wiggle around when it's crying. And my description of the baby computer doesn't reference any of these biophysical or biomechanical processes. So it's just operating at a level of abstraction. Maybe those details matter. Maybe when we specify what the crying state is, we say the crying state consists of these biomechanical processes, tear ducts, leak water, and so on. Or maybe we leave this as a very high level of abstraction and we have some other states for these more specific biomechanical processes. Exactly what level of abstraction we're using to describe the baby, to explain the baby's behavior, will influence whether or not we consider some explanation mechanical or not. So at this very abstract level, it's really hard to see how the baby's not a computer because this is what it's doing. The transitions between here are fairly easy to see because it's a very high level of description. Maybe if we were more detailed about what the baby's doing at a biophysical level, these descriptions would not be as straightforward. So part of saying that the baby's a computer is also deciding what level of abstraction we want to describe and explain the baby's behavior. And this is another reason why I don't like the idea that babies are not computers. The argument that babies are not computers is saying that not only can you not explain the baby's behavior, but you can't explain the baby's behavior at any level of abstraction. Right, so you might say that the baby's behavior is explainable at this level of abstraction, but not that level of abstraction. But to say that babies are not computers at all is to say that there's no level of abstraction that you can give to fully explain the baby's behavior. That babies just defy explanation, which is just to say that they're miraculous. And maybe you can have that view. That's fine. I'm not going to hold it against you. But it does seem to me like a dualist view, a view that thinks that brains work fundamentally different from everything else in the mechanical universe. And that makes it really hard to see how science can make any headway in explaining how the mind works. Okay, so those were different arguments for thinking machines, that machines can think. Obviously, that's not the complete story, but I want to actually go back to Turing's test. Because Turing, halfway through his paper, says that he thinks the original question, can machines think, is too meaningless to deserve discussion. So Turing's view in the paper is not that machines can think, and here's what he means by thinking, and machines can do that thinking process. He says explicitly that he believes the question, can machines think, is too meaningless to deserve discussion. So then what is he doing in this paper? What is the Turing test for? It's not about giving an argument that machines can think. It's instead giving an argument about our educated opinion, sort of what we think about machines. And this is what the Turing test is designed to show. So let's talk about the Turing test explicitly now. So the way the test works is based on the Imitation Game. The Imitation Game is an old parlor game that people used to play, like at dinner parties and stuff, before you had TVs. So the way the game works is that you have a big dinner party, you have one man and one woman from the dinner party go off into another room. And then the rest of the dinner party's job, the game, is to ask questions of the two players. One you call A and one you call B, so you don't know their names. You ask questions of both players and you get the responses, and the responses are usually written out so that you can't read their handwriting or anything. But just from the content of their responses, the question is, can you distinguish the male from the female, the man from the woman? Can you tell which one is the man and which one is the woman? Just by asking these questions of people you can't see. This is sort of a parlor game. Maybe the answers get a little bit sexy because you're talking about gender, and maybe it's sort of a kind of a fun, sexy dinner party game. For several years teaching AI at a academic summer camp, I had students play the gendered version of the game. High school students, where one boy and one girl in the class would go outside, and the rest of the students would ask questions to figure out which one is the man, which one is the woman, which one is the boy, and which one is the girl. And in the class, and this is part of the point of the exercise, very quickly you saw the students start appealing to gender stereotypes for asking their questions. Like they would ask the person they thought that was a boy, they would ask them, what is your favorite video game? And the person that's a girl, they would ask, what's your favorite brand of makeup? Or what's your favorite brand of shampoo or something like that? And these style of questions obviously reflect something about the gender biases that we have, that boys do certain things and are identifiable by certain factors, and girls have other traits and are identifiable by certain factors. Right? So asking the boy, what's your favorite video game? Right? The idea is that girls are not going to have favorite video game, or they're going to have a very specific set of video games, and you're going to be able to tell the difference between the two just by what video games they play. Now, obviously, this isn't true. Some girls like video games that are stereotypically boy games, and vice versa. Some boys have a favorite makeup or a favorite shampoo. So these kinds of questions are not definitive in distinguishing between the boy and the girl. And when I played this game with my high school students at the summer camp, they see very, very quickly that not only does this game rely on stereotypes, but you're never going to get a certain answer out of it. Like it's you can be fooled fairly easily. In the Imitation Game, I think one of the people is trying to fool you. So like maybe the woman is always telling the truth and trying to give the correct answer to convince the party that she's a woman, but the man is giving wrong answers and trying to convince the party that he's a woman. And so being able to distinguish not only the gendered answers, but also to distinguish who's lying and who's telling the truth as part of the game. So this is the imitation game as it was played before Turing, and Turing says, well, why don't we play the same game but with a machine? Why don't we have the computer take place of one of the participants? And Turing is never actually explicit about whether we're supposed to play the gender game with the machine, but the way that the Turing test has come to be taken is that the goal is to see if we can distinguish the human from the computer. So just like in the gendered imitation game, you're asking questions, you can't see them directly, but you're just getting the responses. The responses are typed out, so you can't tell the difference between handwriting or whatever. And the computer is trying to convince you that it's a human, and the human is also trying to convince you that it's a human, and your job as the judge is to determine which one is which. The computer passes the test if you come to believe that it's human, if you miscorrectly identify it, if you incorrectly identify it. If you say that A is a human, when in fact that A is a computer, then the computer has fooled you into thinking that it's human, and so it passes the Turing test. The goal here is indistinguishability. One way of framing this goal is that the goal is to trick the judge, but this is maybe a not very generous way of describing the test. Maybe the more generous way of describing the test is that the goal of the test is to get the computer to behave indistinguishably from a human. In other words, get the computer to behave just like we would expect a human to behave in this question and answer session. Right? If the computer is giving answers of the sort that we would expect from another human, such that we can't tell that it's a computer at all, then Turing says that it passes the imitation game, and so that we should judge that it's intelligent. Turing's argument is that, this is how we judge the intelligence of people, right? If I want to figure out if some person is intelligent, I start asking them questions, and if they give me intelligent answers to those questions, then I think they're intelligent. And if they give me a bunch of dumb answers to those questions, then I think they're not very intelligent. Maybe a good example here is to distinguish. So I have a sister that sleepwalks, or at least when we were kids, would have these sleepwalking sessions where she'd get up in the middle of the night and just walk around the house. And it's a little bit creepy. And the weird thing about it is that she's not conscious during it. Right? She's not making decisions as she's sleepwalking. She's fast asleep, but she's walking around. And so you walk up to her and you start asking her questions. Hey, Davy, are you okay? Do you need any help? Are you asleep? And she just doesn't respond to it at all. And this is not how a person who's fully awake would respond, right? So I can tell that something's up from my sister sleepwalking because I'm asking her questions, and she's not responding the way I would expect a fully conscious, awake human would be responding. She's responding, in fact, like the way that I expect a sleepwalking person to respond, and that's different, and I can distinguish those two. Similarly, maybe you would expect the computer to make all sorts of mistakes, maybe mistakes about popular culture, or mistakes about what human preferences are. So if you ask it questions and the machine is answering in a way that is very clearly not human, so you can tell that it's not human, then maybe it's not very intelligent. But if the machine is doing everything that makes you think that it's an intelligent person, so that you think it's an intelligent person, and it does this in a way that you can't tell that it's a machine, then Turing says that we should consider that machine intelligent. After all, this is how we judge another person to be intelligent. When that person performs a task, we judge the person to be intelligent. So if the machine can perform the same tasks, if the machine behaves in the same way, then we should judge the machine intelligent also. Now, there's a lot of ways of reading this test. This is the basic setup of the test. And remember, Turing predicts that by the year 2000, computers will be able to engage in 5 minutes of conversation and pass this test about 30% of the time. Very low bar to meet. We've since have computers that are passing this test much more regularly. Sometimes nowadays, if you call a customer service line, sometimes it's hard to tell at first whether you're talking to a machine or a human, because you can talk to it in natural language. You can actually say things to it and it will respond to you. And sometimes it's a human, sometimes it's a machine, and sometimes it's hard to tell the difference between the two. But there's lots of ways of interpreting Turing's test. So one way of interpreting Turing's test is to say that what Turing is saying is that what it means to be intelligent is to behave like a human. So human behavior is the standard of intelligence, and machines are intelligent when they meet us in our level, when they get on our level, when the machine can do the things that humans do. Then we should consider the machine human we consider the machine intelligent because the things that humans do are intelligent. And so when the machines are doing what we do, then the machine is intelligent. And so the Turing test on this reading is a test designed to see if the machine can do what we do. And if it can perform the way that we do, then we judge it to be intelligent. Because whatever we do is intelligent. So by definition, the things that humans do are intelligent. So that's one way of reading this test. This is not a very good reading, I don't think, because I don't think that Turing is giving a strong theory of what it means to be intelligent. I don't think this is Turing's goal here. I don't think that Turing is defining intelligence as whatever it is that humans do. And I don't think Turing is saying that simply if a machine can do whatever humans do, then we should consider it intelligent. Instead, here's another reading of what Turing is doing. So, that first reading that I gave, that the goal is to get machines to behave like us, this is a very popular reading, especially among philosophers. And you might think that, well, part of the problem is that the machine is only behaving like us in a very specific way, and that it's using language, it can answer questions. But that's not all that it means to be human. Humans can do more than just answering questions. So maybe if you have a machine that can also run a marathon, maybe if you had a machine that can also engage in sexual reproduction and reproduce and have its own children, like maybe these are the kinds of things you need to be able to do in order to be intelligent. So the computer can't do that. Maybe it can use words to fool us that it's intelligent, but it can't do all these other things. But you can expand the Turing test to just include these other things. There's the so-called total Turing test, where the machine doesn't just speak like other humans, doesn't just use language like another human, but does everything like another human. All anatomical or physiological behaviors are reproduced in the total Turing machine. So the total Turing test tests sees the machine is indistinguishable in every single way. Maybe even to the point where if you draw blood, the blood is recognizably human and has the correct body temperature and all that kind of stuff. After all, that's how we test human beings to see if they're okay. Maybe the machine also has to stand up to scrutiny along these tests in order to be considered intelligent. So all of these are ways of imagining intelligence as a sort of criteria and seeing if the machine meets this criteria. But I think this is actually a bad way of reading Turing's test. It's the standard way, that's how most people read the test. But I think this is actually a bad way of reading the test. And I want to select a different way of reading the test. And this is on the basis of fair play for machines. So this is a quote that Turing doesn't use in his 1950 paper, but it comes from his a lecture he gave to the London Mathematical Society in 1948, I believe. And in this other paper, he's talking, it's clearly a run-up to the Turing's test. He's talking about different ways of evaluating the intelligence of machines. And one of his proposals is to have machines that play chess. And his idea is that if you can build a machine that plays chess, well, playing chess is a kind of intelligent activity. Only intelligent humans can play chess. So if a machine can play chess and beat humans at chess, then maybe this is a fair way of evaluating the machine's intelligence. But what he's really interested here is not just find a method for evaluating intelligence, not just find a definition of intelligence, but really find a fair way of evaluating intelligence, to judge the intelligence of machines fairly. And what he's particularly worried about is prejudices that humans have against machines. Turing is concerned that just because we see that it's a computer, we'll automatically conclude that the machine is not intelligent, that it's not doing something intelligent because it's a machine. In other words, Turing is worried about prejudices against machines, that we're systematically biased against machines so that nothing the machine can do would be considered intelligent. It doesn't matter how clever the thing it performs, it doesn't matter how hard the thing to do is. Like, I can't beat Kasparov at chess, right? I'm a much worse chess player than what Deep Blue is, but I might still think that Deep Blue isn't intelligent, and my judgment here is not based on what the machine does, because it's obviously doing something very impressive, but instead it's based on what it is. I'm saying that it's a machine just because it's a machine, it's not intelligent. And Turing thinks this isn't fair. It's judging the machine by a different standard. So what I want to say that Turing's test is designed not as an accurate measure of intelligence, but as a method of fairness, as a method of stripping away human biases. Right? The idea is that if we're judging the machine in this way, then we can't simply disregard the machine simply because it's a machine. Right? We won't simply see it's a computer and say, well, it's not intelligent. We have to actually look at its behavior, and if the linguistic behavior is enough, then maybe that's enough of a sign of intelligence. Again, because after all, this is the same criteria we use to judge the human. When the human is able to use language in a way that looks intelligent to me, then I judge that human being intelligent. And when the human plays very good chess to beat all the world champions, I judge that human to be intelligent. So when a computer beats the world champions, why shouldn't we judge the computer to be intelligent as well? Anything else is unfair. Anything else would be a double standard. To say that Kasparov is intelligent because he plays really good chess, but to say that Deep Blue is not intelligent, even though Deep Blue plays really good chess, simply because Deep Blue doesn't do other things, like Deep Blue can't enjoy sunset, or Deep Blue doesn't like art, or doesn't have a favorite movie. That's true, Deep Blue doesn't have those things, but you've shifted the goalposts about what things the machine has to do. Now it's not enough to do the one intelligent thing. Even though when Kasparov plays chess and we consider Kasparov intelligent, we don't ask about whether Kasparov likes art or does other things. Like, we assume he does those other things, but even if he doesn't, the fact that Kasparov plays good chess seems to be enough to consider Kasparov intelligent. And when Deep Blue beats Kasparov at chess, and we don't consider Deep Blue intelligent, Turing just thinks this is a double standard. It's not fair that we're simply engaging in our biases against machines. So the point of the Turing test is to get us rid of our biases, to give the machines a fair chance, to give the machines a test where they actually have a shot at winning and where our biases aren't just excluding them from the outset. I think this is really the key for all of thinking about artificial intelligence and for thinking about thinking machines, is that our basis of evaluation fair? Are we judging the machine based on fair standards? Or are we judging the machine on standards that aren't fair, that we don't apply to ourselves? Okay, that's the Turing's test. There's a lot more to say about Turing's test. Again, I strongly encourage you to read the paper itself and look at some of these objections. But there's one major objection, this is the last thing I'll talk about here, that gets brought up around Turing's test. So there's an explicit objection by a philosopher named John Searle. This was in a paper called Minds, Brains, and Programs, written in 1980. This is during the AI winter, so there's not a lot of development of artificial intelligence happening at this time, but Searle picks this time to give an argument against the very possibility of machines thinking. So Searle's argument is very similar to the argument from consciousness that Turing considers in the paper, but here's how Searle's argument works. So Turing says that if you can build a machine that uses language convincingly, that talks like a human, that speaks like a human, then we should consider intelligent. But Searle's Chinese room is supposed to be an example of a machine that can use language apparently intelligently, but that there's no intelligence going on inside, or what Searle says, the machine understands nothing. He says the machine understands nothing, it's not in that line of business. And here's how he gives the argument. So he imagines a Chinese room. So the Chinese room is this room that Searle is in. And the room has inputs and it has outputs, and it's got, on the inside, it's got a big database with a bunch of rules. So Searle's in there. Searle's a normal human being. And Searle speaks English fluently. He speaks German and French not as well, but he can read it. He is a little bit of familiar with those languages. But he doesn't speak Chinese at all. He knows nothing about Chinese symbols. He doesn't know how to translate them all. He says, to me, they're meaningless squiggles and squaggles. So Searle understands nothing of Chinese. But he's in this room, and the room is set up with this rule book that tells you how to manipulate Chinese symbols. Now, importantly, the rulebook does not tell you how to translate these symbols. Nothing inside the Chinese room gives you translation of Chinese characters. Instead, what you do is just you have a relationship between the input and the output, an if-then go-fi structure. So the rules in Searle's rulebook look like this. If you see this shape followed by this shape followed by this shape, then produce this shape followed by this shape on the output. Right, so Searle gets these input characters. He doesn't know what the characters mean, but he has these rules, and notice the rules are written in English. Right, so follow these rules, and the rules require not understanding the meaning of the Chinese symbols. It just requires pattern matching. Right, so here's a couple of symbols. I don't know what they mean, but I can see if they match up with any of the symbols in my rulebook. And if they do match the symbols in your rulebook, then the rules tell you certain symbols to put on the output. So Searle's getting Chinese symbols in, he looks up in his rulebook what to do with those symbols, and then he produces other symbols to put as output. The entire time, Cyril says, I have no idea what Chinese means, and following these rules isn't giving me any insight into what these words mean. No matter how much I'm following these rules, the words are still squiggles and squaggles. I have no idea what the words mean at all. I don't even know if they have meaning whatsoever, but I still know how to follow the rules, because the rules don't require understanding the meaning. It just requires understanding the shape of the symbols and sort of following the patterns required. And anyone who knows how to do pattern matching can do that. You don't need to know what the language means. You just need to know how to do the patterns. But Cyril says, so I don't understand what the Chinese symbols mean, but it might be that anyone outside this room who does understand Chinese will be interacting with the room such that it seems to them that they're giving sensible Chinese inputs on the input, and maybe these inputs are questions in Chinese. So it seems to the people outside the room that I can give the room a sensible question in Chinese, and it responds to me with a sensible response that seems seems related to the question that I asked. It seems like an intelligent response to that question. So in other words, from the outside of the Chinese room, it looks like whatever's inside the Chinese room can speak Chinese. It looks like they're passing the Turing test. You can give them questions, they give you sensible answers, they give you the answers that you expect from any human performance. But on the inside, Cyril is following these rules, and he can't speak a lick of Chinese. He doesn't know anything at all about Chinese. The words are completely meaningless to him. And Cyril says, Cyril's argument is that this shows that the Turing test is not enough. This shows that something that follows rules to produce convincing behavior can still completely lack understanding on the inside. Cyril doesn't understand anything about Chinese, but he can follow the rules just fine. And imagine he does it fast enough. Imagine he gets good enough with the rule book that he's giving fast enough answers so that there's no lag in time, so that you're giving it. The people outside are giving sensible Chinese questions, and they're getting responses in the time frame that you'd expect a human being to respond. And so people on the outside are going to say, look, this is passing the Turing test. It's speaking like a normal human. It's behaving indistinguishably from human. And so obviously it's intelligent and understands Chinese. But Cyril says, but look, I don't understand Chinese at all. So obviously there's no understanding in the room. There's no understanding of Chinese in the room. If people outside the room believe that the Chinese room understands, that's sort of a creative mental act on their part. They're imposing that view on the Chinese room, but there's no actual understanding there. And then Cyril says, but look, this is exactly what computers do. Computers just follow rules. They're just doing pattern matching, sort of symbol matching, symbol manipulation. Cyril calls it syntax rather than semantics. My CPU is following a bunch of simple instructions for manipulating binary code. It doesn't understand what any of those instructions mean. It doesn't understand what the code represents. It doesn't understand anything in the outside world. It just performs these simple syntactical operations. But Cyril says, but syntax is never enough for semantics. Semantics is the meaning of the words. And Cyril says no amount of manipulating these symbols is enough to understand the meaning. And if computers are only manipulating syntax, then computers are never going to have understanding. So computers are completely limited from semantics. So Turing test isn't enough. Turing test doesn't show us that the machine actually understands what it's doing. It just shows that it can follow rules, but following rules is not enough. This is Cyril's argument. Cyril, just like Turing, Cyril never exactly tells you what thinking is or what understanding is. He never tells you why he has it and why he has it of English and why he doesn't have it of Chinese. He doesn't tell you how it works. He just says it's obvious that I don't understand Chinese, that there's no understanding in the Chinese room. Even if there's rule following, that rule following is not enough for understanding. It's also obvious that rule following is all that the computers are doing, so the computers understand nothing. They're not in that line of business. So Cyril gives this thought experiment, and instead of justifying the view of understanding or the view of intelligence, he just jumps straight into objections, again, similar to Turing's paper. I just want to look at a couple of these objections. So one objection is that maybe the problem here is with the language. Maybe the problem is that the only inputs that Cyril has are language items. The only outputs he can give are linguistic items. What if we gave more sophisticated inputs? What if the inputs were like full video and audio from the outside world? And what if the outputs were not just verbal outputs, but what if Cyril could also like move around? Like he was, in other words, what if Cyril was in a robot that he could control, could move around the world, could get visual and auditory input, tactile input, and use these other kinds of inputs and other kinds of actions in the world in order to develop its understanding? Is that enough? If the Chinese room were a robot, would it understand? And Searle says, no. You can give it all sorts of fancy sensors and so on. You can give it all sorts of fancy motors for moving around. But in a computer, all those motors and sensors are eventually converted down into binary code. And what the computer is ultimately doing is doing these manipulations of binary code. And so even if you make it a robot, the robot is still just a computer and is no possibility for understanding in that computer. So making the room a robot is not going to help. One other reply, though, and I think this is a good reply, is to say, well, look, Searle, you're not the only thing that's going on in this room. This is the system's reply. The system's reply is that Searle doesn't understand Chinese. Okay, Searle, you don't understand Chinese, but there's a lot of other stuff going on in this room. In particular, there's this whole rule book and data set, and maybe that's where all the understanding is, right? Like maybe you need to understand Chinese really well in order to have a rule book that associates certain inputs to certain outputs. Like building this rule book is already going to encode all of the Chinese understanding into the room. So yeah, you don't see any understanding in Searle's head, because that's not where the understanding is. The understanding is in the paper. The understanding is in the rules that Searle is following. So Searle doesn't understand Chinese, but you might think the whole room understands Chinese, or Searle plus the rules together have combined understanding of Chinese. So when the people outside say, oh, looks like the room understands Chinese, they're actually right. Searle is maybe the CPU, and Searle doesn't understand Chinese, but the whole system taken together, including the data, including all the rules and programs, that's where the understanding lies. Now, Searle thinks that this argument is absurd. He thinks, look, if I don't have understanding, then me plus bits of paper isn't going to increase understanding. But Searle says, okay, fine. Maybe the rules are where the understanding is, but we can expand. I mean, the thought experiment is already pretty absurd. So imagine we expand the thought experiment so that Searle memorizes the rule book, and the rule book goes entirely into Searle's head, so he's not actually referring to something out in the world, but he's just referring to these rules that he's memorized. And Searle says, even still, I won't understand Chinese. I'm still just following rules. I still don't understand Chinese, even if I'm following rules fast enough so that I can respond. So this is why Searle's response here is difficult to swallow, because if I've internalized that entire rule book and I'm responding at a rate that seems human, in other words, if Searle that has memorized this rule book can go out into the world and hear people talking in Chinese and then give appropriate responses in Chinese in the same time frame that a normal human would respond to Chinese. In other words, behaviorally, Searle understands Chinese. He's saying all the right things. He's responding in the right way to other people talking in Chinese. From all behavioral indications, it looks like Searle understands Chinese. And then Searle's still insisting that he doesn't understand Chinese at all. And it's not clear what that insistence amounts to. If you're behaving in all the right ways, what else is there to understanding but responding in all the right ways to other people, using the language, and so on? I want to say that the understanding can exist in the book. It can also exist in Searle's mind if he memorizes the book, but it can also just exist out in the world. That our intelligence isn't all in our head, but it's also in the tools that we use and the way that we construct our worlds. And so if intelligence can be in this book, then maybe the Chinese room is intelligent. Maybe the Chinese room does legitimately pass Turing's test. I think this is part of the trick in general is thinking about the agency of our artifacts and sort of what they're doing to augment our intelligence. But this gets into some of the ethical concerns that will come in our next section. So I'm going to put myself back on screen. I think that's the last slide. Yeah, thank you. Thank you very much for listening. I'm way over time. This is 2.5 hours. My throat is sore from talking so much, and I hope that wasn't too boring. This definitely needs to be edited down in the future, but this is the discussion. Hopefully we can talk about this in class over the next few days. Thank you very much. Talk to you later.